Good morning, sir.
Hello. Please respond. Nurse Ongol.
Sir, good morning, sir.
Good morning, sir. VS Krishna, please respond. VS Krishna, please respond. VS Krishna.
Sir, VS Krishna respond, sir.
Okay, sir. Anantapur.
Yes, sir. Sir, response, sir.
VS Krishna, okay, sir. Anantapur.
Anantapur, yes, sir.
Okay, sir. Kadapa. Kadapa.
Good morning, sir. Kadapa responding, sir.
Morning, madam. ఒకసారి మాట్లాడండి మీరు.
Good morning, sir. You are responding.
సార్ ఓకే ఆడియో.
Okay, thank you, sir.
ఓకే సార్.
Good morning to all. Are we ready for the second lecture?
Good morning, sir.
Yeah, please tell me when to start.
Yes, sir. Start, sir.
I can-
Sir, ready? Please give the reply.
Okay, so let me share my screen.
Yes, sir. Other agencies, please respond.
Can you see my screen? Oh,
Yes. Yeah.
right. So let me recall. I had defined a map from Z plus dot to Zn plus n dot n. X going to the remainder when X is divided by n. Let me write it down. X going to the remainder when X is divided by n. This was a ring homomorphism. And then Z and T for any natural number T is contained in Z. I can restrict Rn to Z and T. This Rn is also a ring homomorphism from Z and T plus Nt dot Nt. Right? This is addition modulo multiplication modulo. This is also a ring homomorphism. Now, I can extend Rn to Zx, the ring of polynomials, with coefficients in Z. Extend Rn to Zx from Z to Znx. This ring of polynomials with coefficients in Zn. I can extend Rn, and how do I extend? A naught plus A1x plus so on plus a L XL. This maps to RNA naught plus RNA1 X plus RNA2 X squared plus so on plus RNAL XL. And you can check that this is also a ring homomorphism. A ring homomorphism. Okay. Yeah. So I want to prove Lagrange's theorem for polynomial congruences. So first of all, I'm going to take n equal to p a prime. Let n equal to p a prime. So I get Rp from Zx. By abuse of notation, the extension to the ring of polynomials, we just call it the same Rn. So this is Zpx. Zpx. Now, before I continue, I want to say a few general things about. So let me just diversion. So let F be a field. Let F be a field. Incidentally, recall that Zp plus P dot P is a field. Let F be a field. Let F of X equal to A naught plus A1x plus so on plus ALXL belong to F of X. Now, for any A in F, look at F of X minus F of A. This is equal to A naught plus A1x plus so on plus ANXN minus A naught plus A1A plus A2A squared plus so on plus AL A to the power of L. So the A naughts will cancel and I'll have A1 into X minus A plus A2 into X squared minus A squared plus so on plus AL, sorry, it's XL minus, should be L, XL minus AL. Now you know that x minus a divides x to the t minus a to the t for all t in n, right? Because x to the t minus a to the t is equal to x minus a into x to the t minus 1 plus x to the t minus 2a plus x to the t minus 3 a squared plus so on plus a to the t minus 1. So each one of these terms is divisible by x minus a, and therefore fx minus fa is divisible by x minus a. So therefore fx minus fa is divisible by x minus a, i.e. there exists some qx in fx such that fx is equal to x minus a into qx plus f of a. Actually, this is the division. This is a special version of the division algorithm for fx when the divisor is x minus a. I only need this, so I'm not going to go into the general proof of the division algorithm. All right, so therefore, if a is a root of f of x, that is, f of a is 0, then I get that a1, that is f of a1 is 0, then I get that f of x is equal to x minus a1 into some q1 of x. Now, if a2 not equal to a1 is another root, then I get that 0 is equal to f of a2 is equal to a2 minus a1 into q1 of a2. So this implies that q1 of a2 is equal to 0. So a2 is a root of q1. Therefore, q1 of x is equal to x minus a2 into some q2 of x, and so on, and so on. Now recall, so if I have another root a3, then I can, so if a1, a2, as are distinct roots of f of x in f, then I have f of x is equal to x minus a1 into x minus a2 into x minus as into some, say, q of x. So degree degree of f will be equal to degree of each one of these x minus ai is 1. And you know that the degree of the product of two polynomials is the sum of the degrees. I'll write that down here. Degree of ux vx is equal to degree of ux plus degree of vx. It's the sum of the degrees. So then I'm going to get s plus degree of q. So from this, it's clear that s must be less than equal to degree of f. So conclusion, final conclusion is a polynomial of degree n in f of x cannot have more than n roots in f. A polynomial of degree n cannot have more than n roots in f. Now, what I want to prove is Lagrange's theorem. So let me state the theorem. Lagrange's theorem. Lagrange's theorem for polynomial congruences. And what it says is that if f of x is a polynomial in ZPX of degree n, then f of x cannot have more than n roots in ZP. Okay, so that's just an immediate follows from the my previous conclusion, because ZP is a field. So the congruence version of this theorem is as follows. The corollary, let fx be a polynomial in Zx of degree n. Then there cannot be more than n solutions mod p to fx is congruent to 0 mod p, because and reason to say that f of alpha is congruent to 0 mod P is the same thing as saying uh, that RNF of Rn alpha is equal to 0, i.e. Rn alpha is a root of RNF. Yeah, I should remark that remark sorry remark Rn of F alpha is equal to RNF of Rn alpha. Actually, in most books, instead of Rn, they write bar. You know, they write Rn alpha as alpha bar, but this doesn't tell you what it is mod. It is assumed from the text that it is mod n or mod whatever. So, I prefer this Rn remainder when divided by n because it tells you what mod you're taking. So, yeah, let me just show this. Suppose f of x is equal to a naught plus a1x plus a l x l, then f of alpha will be a naught plus a1 alpha plus so on plus a l alpha l. So Rn of f of alpha, remember that Rn is a ring homomorphism. So it will be Rn of a naught plus n Rn of a1 into here the into means dot n Rn of alpha. Remember it's a ring homomorphism. So on plus Rn of al of Rn of alpha to the n plus n plus n. So this is nothing but Rn of f of Rn of f. So from all this, you can see that you know basically over a field, a polynomial of degree n can't have more than n roots in the field, and from that, if you do the language mod p and remembering that a field Zp is a field, you get that the number of solutions mod p of f of x is equal to 0 mod p cannot be more than n mod p. So that's all what Lagrange's theorem is. Now I want to prove one theorem about general theorem about fields, which I'm going to need when I do the Legendre symbol. What I want to prove is the following. Let f plus dot be a field with additive identity 0. Then we know that F minus 0 dot is an abelian. Okay, that's if you recall my definition of a field yesterday, this was part of the definition. So let G be a subgroup of F minus 0. Let G dot be a subgroup of F minus 0 dot and assume that G is finite. So I hope you get what I'm. Let G be a finite subgroup of the multiplicative group of non-zero elements of a field. I'll repeat that. Let G be a finite subgroup of the multiplicative group of non-zero elements of a field. Okay. Then my theorem is G is cyclic. G is cyclic. So a finite subgroup of a multiplicative group of non-zero elements of a field must be cyclic. Now for this, I need a lemma. So yesterday we showed that if M and N are co-prime, then phi Mn is equal to phi M into phi N. Okay. Now define f of n to be equal to the sum of d dividing n, phi of d. So for example, suppose n is 6, then divisors of 6 are 1, 2, 3, 6. Therefore, f of 6 is equal to phi of 1, which by definition is 1, plus phi of 2, plus phi of 3, plus phi of 6. So I hope the definition of Fn is clear. Now, something about phi. If n is equal to p, a prime, then it's clear that phi of p is equal to p minus 1 because Zp cross is just 1, 2, up to p minus 1, which has p minus 1 element. So the cardinality is just p minus 1. If n is equal to p to the power of e, p a prime, then what is phi of p to the power of e? This is equal to the cardinality of the set of I 1 less than equal to I less than P to the E, the cardinality of this, sorry, I forgot to say, uh, such that IP is equal to 1, which is, okay, so this is, so what are the elements who in ZPE whose GCD with P is 1? Whose GCD with P is 1. So this is equal to P to the E minus all multiples of P in ZPE, right? It's the complement of the set where IP is not 1. And if IP is not 1, it means it must be a multiple of P. So this, how many multiples of P are there in ZP to the E? They are P to the E minus 1. So this is equal to P to the E minus P to the E minus 1 is equal to P to the E minus 1 into P minus 1. Okay, so, and then because phi NM is, when N and M are co-prime, so if N is equal to P1 to the power of E1 to the PR to the power of ER, PI distinct primes, then phi of N is equal to phi of P1 to the E1 into phi of P to the E2, because these are all co-prime to each other, into phi of PRER, which is equal to P1 to the E1 minus 1 into P1 minus 1, and P2 to the E2 minus 1 into P2 minus 1, so on, PR to the ER minus 1 into PR minus 1. So I can, for any N, I can compute what phi of N is. Now I want to look at F, this F of N. My claim, so my lemma is, if M and N, if M and N are co-prime, that is, GCD of M and N is 1, then F of Mn is equal to Fm into Fn. Okay, this is one. So what holds for phi also holds for F. So let us give a proof of this. Proof. Let M be equal to E1 to the E1, PR to the ER. This is the prime factorization of N. And N equal to Q1 to the F1, to the QS to the FS. And the PIs and the QIs are distinct. Because GCD of M and N is 1, the PIs and QJs are distinct. No PI can be any QJ and no QJ can be any PI, are distinct. See. So now suppose D divides Mn, which is equal to P1 E1 to the PR ER, Q1 F1, QS FS. Then D will be a product of some P's and some Q's. So D will be a product of some P. So if the P part, D will be a product of some powers of PIs, that is the GCD of D and M, and a product of some powers of QJs, i.e. Dn. Dn. So what we'll get is that D is equal to Dm, the GCD of Dm into the GCD of Dn. That's what we'll get. So if I can call this D1 and I can call this D2, then D1 divides M and D2 divides N. And you can see from this that I now make a statement. Every divisor of Mn can be uniquely written as a product D1, D2, where D1 divides M and D2 divides N. See, here the fact that the P's and the Q's are completely different from each other is very important. Okay, so now F of Mn is equal to sum D dividing Mn of phi of D. That is equal to, by this above remark, sum D1 dividing M, D2 dividing N of phi of D1, D2. Now, if M and N are co-prime, they don't have a common factor other than 1. And if D1 divides M and D2 divides N, then D1 and D2 will also be co-prime. So this will be equal to sum D1 dividing M, D2 dividing N of phi of D1, phi of D2, because D1 and D2 are co-prime to each other. Because D1, D2 will be co-prime equal to 1. So now I have separation of variables. So this is equal to sum D1 dividing M, phi of D1 into sum D2 dividing N of phi of D2. That's equal to Fm into Fn. So, yeah, so this is that. So now, Let me prove the theorem, proof of theorem. Proof of theorem. Proof of theorem. What is the theorem? Let me recall. G is a subgroup of F minus 0 dot G, and G is finite. G is finite. I want to show that to show G is cyclic. Okay. For let me give the let the order of G be n. That's what I want to say. I give let order of G be equal to n. Now, by Lagrange's theorem, we know that the order of any element in G will be a divisor of n. By Lagrange's theorem, we know that the order of any element in G will be a divisor of n. So, if D divides n, define G of D to be the set of X in G such that the order of X is equal to D. Now, be careful. I'm not saying that GD may be empty. I'm not saying that for every divisor of n, there's necessarily an element of order D. But if there is, then all the elements of order D, I call them G of D. So I'll make I'll say G of D may be empty. May be empty. There may be not be any element of order D. G of D may be empty. Okay. Suppose G of D is not empty. Suppose G of D is not empty. So let X belong to let X belong to G of D. Then cyclic group generated by X is 1 X squared up to X to the D minus 1. And order of X is D. Order of X is D. That's what the definition of G of D is. Those X whose order is D. So let X is D. Then the cyclic group generated by X is this. And these are all distinct. So these elements are all roots of the polynomial X to the D minus 1 belonging to f of X. But Now these are D different elements, and they're all, and I know that XD minus 1 cannot have more than D roots. Therefore, the elements 1 x xd minus 1 are precisely all the roots of xd minus 1 in F. So therefore, see, any element of order D, will be a root of xd minus 1. So therefore, G of D is contained in 1 x squared xd minus 1. Because any element of order D will be a root, and these are all the roots. There are no other roots. Okay. So the question now is, in this set, in the set, 1 x squared xd minus 1, what are the elements? What are the elements of order D? Right? X has order D, but some powers of X may also have order D. I.e., what are the I 0 less than I less than D? What are the I such that order of X to the I is equal to D? So order of X is D, but I'm now asking what are the powers of X which also have the same order D? I'm now going to use we know that order of X to the I is equal to this is a result from group theory. Order of X divided by the GCD of I and the order of X. Okay, this is equal to D divided by ID. Okay, so therefore, order of X to the I will be equal to D if and only if ID is 1. ID is 1. Okay, so the elements of order D in G are all X to the I 1 less than equal to I less than D, such that I D is 1, and the cardinality of this set is precisely phi D. But the cardinality of this set but by definition of phi d, uh, cardinality of x to the I, cardinality of x to the I, 1 less than equal to I less than d, such that ID is 1. Cardinality is phi d. Therefore, cardinality of GD is 0 or phi d. Cardinality of 0 is 0 or phi d. If GD is empty, then it is 0. And if GD is not empty, if there's an X in it, then the cardinality of GD would be phi d. Now, my claim is that Fn is equal to n for all n. So, suppose n is equal to P1 E1 to PR ER, then f of n is equal to f of P1 E1, f of P2 E2, and so on, f of PR ER. Because the different powers of P are co-prime to each other. And we showed that f of Mn is equal to Fm into Fn when M and N are co-prime. So what is f of P to the power of E where P is a prime? So this is sum of I from 0 to E phi of P to the I. Because the divisors of P to the E are precisely 1, P, P squared, P cubed, P to the power of 4 and so on up to P to the E. So this is equal to that. This is equal to phi of 1 is 1 plus phi of P is P minus 1 plus phi of P squared is P squared minus P plus so on up to P to the E minus P to the E minus 1. So this 1 will cancel with 1, P will cancel with P squared will cancel with P squared, and finally only P to the E will be left. So f of P to the E is P to the E. Therefore, f of n is equal to P1 E1 to PR ER, which is equal to n. So f of n is equal to n. Example, just to make an example, f of 6 is phi of 1 plus phi of 2 plus phi of 3 plus phi of 6. This 2 into 3. This is equal to 1 plus 2 minus 1, 1 plus 3 minus 1, 2 plus phi 2 into phi 3. That is equal to 4 plus phi 2 is 1, phi 3. So 4 plus 2, that's 6. So this is an example of that. All right. So now we have G is equal to union of GD D dividing N. Right? Because the order of any element has to be a divisor of n. So it has to belong to any element in G. G has to belong to one of the GDs. And of course, all the GDs are contained in G. And this is a disjoint union. It's D over disjoint. Disjoint union. Because an element can't have two orders. Right? GD1 are the elements of order D1. GD2 are the elements of order D2. But the order of an element is unique. So I can't have an element with two different orders. So this union is a disjoint union. Therefore, therefore the cardinality, therefore n, which is equal to the cardinality of G, is equal to sum of the cardinalities of the GDs. D dividing n. So suppose D1 to DL are all the divisors of n. Then n is equal to cardinality of GD1 plus cardinality of GD2 plus so on plus cardinality of GDL. Now this is 0 or phi D1. This is 0 or phi D2. This is 0 or phi DL. Okay, that we know, which I just now showed that for any divisor D, the cardinality of GD is either 0 if GD is empty, or if it is not empty, then its cardinality is precisely phi D. So, but n is equal to Fn, but n is equal to Fn, which is equal to phi D1 plus phi D2 plus phi DL. So in order to get n, all the phi di's must be there. This means that the cardinality of any GDI can never be 0. Because if it was 0, then in the previous equation, I'll get a 0 as one of the terms. Whereas I require all the phi di's to add up to n. So this implies that cardinality of GDI is not equal to 0 for all I. In particular, cardinality of Gn, one of the divisors of is not 0. In particular, one of the divisors of n is n itself. So Gn is not cardinality of Gn is not 0. i.e. G will have an element of order n, and therefore G is cyclic. Because if I have a group which has an element whose order is equal to the order of the group, then that element is a generator for the group and it's a cyclic. So therefore G is cyclic. So any finite subgroup of the multiplicative group of non-zero elements of a field must necessarily be cyclic. So corollary ZP cross dot P is cycle. So I'm taking here G to be the whole of ZP cross, and ZP is a field, you know that is a field. So ZP cross dot P is cycle. Right, so let us take example. Let me take P equal to 23. Let me try. I don't know what is the cyclic generator, but let me try. So let me try 2. Usually either 2 or 3 work. So I'm going to do everything modulo 23. So I have 2. 2 squared is 4. Then 2 cubed is 8. Then 2 to the power of 4 is 16. Then 2 to the power of 5 is 32, which modulo 23 is 9. Then 2 to the power of 6 is 9 into 2, that is 18. Then 2 to the power of 7 is 18 into 2, 36, that is 13. Then 2 to the power of 8 is 26, which is 3. Then 2 to the power of 9 is 6. Multiply by 2, you get 6. Then 2 to the power of 10 is 12. Then 2 to the power of 11 is 24, which is 1. So, so 2 is not a generator. It's the order of 2 is just 11. So 2 is not a generator. 2 is not a generator. Not a generator. So let us try 3. 3 squared is 9. 3 to the power 3 cubed is 27. 3 cubed is 4. 3 to the power of 4 is 12. 3 to the power of 5 is 36. That is 13. 3 to the power of 6 is 39. 13 into 3 is 39. No, wait, I seem to have made a mistake. 3 to the power of 3 is 27, that is 4. 3 to the power of 4 is 12. 3 to the power of 5 is 36, which is 13. 3 to the power of 6 is 39. Oh, yeah, that is 16. Sorry. Then 3 to the power of 7 is 48, where is 2. Then 3 to the power of 8 is 6. And 3 to the power of 9 is 18. Then 3 to the power of 10 is 54. Modulo 23 is 8. 8. Oh God. 8. And 3 to the power of 11 is again 1. So 3 is also not a generator. And then I'll have to look at 5. So I'm not going to get into it. I was hoping either 2 or 3 becomes a generator, but neither of them is. So one something is going to be a generator. Actually, I'll tell you how to find a generator when I do Legendre symbol. So here I'm just trying to do it by trial and error. Let me continue. Yeah, so look at the map from now I'm going to take P odd. From now on, P will be odd. Look at the map from ZP cross to ZP cross x going to x squared. Incidentally, when I say x squared, I mean x dot px. Please be careful. When I say x squared, I mean x. The multiplication that is involved is dot p. Okay, so that is multiplication modulo p. So look at this map, x going to x squared. This is, I want to look at the kernel of this map. What is the identity of ZP cross? It's 1. What is the kernel? It's easy to see. I should. It is easy to see that this is a homomorphism. This is a homomorphism because the groups are abelian. So xy squared will be x squared into y squared. Xy squared, right? So this is going to be a homomorphism. So what is the kernel of this homomorphism? Kernel is equal to the set of x such that x squared is 1. So it is the solutions of polynomial x squared minus 1 belonging to ZPX. And it's easy to see that 1 and p minus 1 are the solutions. P minus 1, you can call it minus 1 if you want, mod p, are the solutions. Right? A quadratic cannot have more than 2 solutions, and 1 and p minus 1 are the solutions. So, kernel is equal to, I'm going to call it 1 plus or minus 1. Minus 1 means the additive inverse of 1, which is p minus 1. Okay, so kernel is this. Then by the, we know by a theorem in group theory, that if f from G to H is a group homomorphism, then G upon kernel of F is isomorphic to image of F. So therefore, ZP cross by plus or minus 1 is isomorphic to the image. This map I will call it S for squaring map, S. So image of S. And I will denote this image of S by ZP cross squared. These are all the square elements in ZP cross. So therefore, the cardinality of ZP cross by plus or minus 1 is equal to the cardinality of ZP cross squared. Therefore, the cardinality of ZP cross squared is equal to P minus 1. That is the cardinality of ZP cross by 2. So what this is saying is that in ZP cross, half the elements are squares and half the elements are not squares. So what this is saying is, therefore, in ZP cross, half the elements, I'll put in brackets, P minus 1 by 2, are squares, and therefore, half of them are not squares. Okay? So this is that. Suppose, let us, we know that ZP cross is cyclic. ZP cross is cyclic. Suppose alpha is a generator. Then ZP cross squared will be 1, that is alpha to the 0, alpha squared, alpha fourth, alpha 6, etc. All the ZP cross squared will be all the even powers of alpha. That is ZP cross squared. So, yeah. So I'm now going to define the Legendre. Remember, P is odd. Definition. Legendre symbol. So let P be an odd prime. And any integer. Any integer will be defined is A by P to be equal to 0 if P divides A, equal to 1 if there exists an X such that X squared is congruent A mod P and minus 1 otherwise. That means there's no such X. So this is saying this, I want to unravel what there exists an X in Z. There exists an X in Z such that X squared is congruent to A mod P is the same thing as saying that Rnx squared is equal to Rna. The remainder at Rn, Rp. There's no N here. I'm sorry, it should be Rp, not Rn. There's no N. RP. So if I call RP, my P is fixed now. So if I call RPX to be X bar, what this is that X bar squared is equal to A bar. I so so A by P is equal to 1 if and only if A bar is not 0. That is to say that P doesn't divide A bar is not 0, and A bar belongs to ZP star square. It's a square, not P. So, so another way of saying the same thing is therefore A by P is equal to 0 if A bar is equal to 0. Remember, by bar I mean this remainder when I divide by P. 1 if A bar is a square in ZP cross and minus 1 and minus 1 if A bar is not a square. If A bar is not equal to 0 and is not a square in ZP cross. Okay, so this is the definition of the Legendre symbol. So the value of what the value of A by P is depends on what the value of A bar is. What the value of A is mod P. So properties of the Legendre symbol. Properties of Legendre symbol. The first property is that if A is congruent to P, then A by P is equal to B by P. Reason A bar is equal to B bar. You see, the behavior of A by P depends on A bar. And if A and P are congruent mod P, then their remainder when divided by P will be the same. So if A bar is, so that's the first property. It's a kind of obvious property. That the behavior of A mod P determines what the value of the Legendre symbol is. Okay. The second property is that AB by P is equal to A by P into B by P. So, yeah, first I say that if left-hand side is 0, then P divides AB. That means that P must divide either A or B. That means either A by P or B by P must also be 0, and therefore right-hand side is 0. So left-hand side equal to 0 is equivalent to saying that P divides AB, which is equivalent to saying P divides A or P divides B. Remember, P is a prime, which is equivalent to saying that A by P is 0 or B by P is 0, which is equivalent to saying that A by P into B by P is 0. Which is equal to the right hand. So the left hand side is 0 is equivalent to saying that the right hand side is 0. So therefore assume left hand side is not 0. Now, remember that we showed that half the element that see ZP cross squared, the square is a subgroup of ZP cross. And we showed that the half the elements are squares and half the, so it's a subgroup of index 2. It's a subgroup of index 2. So if X is not a square, there are only two cosets. If X is not a square, I have ZP cross is equal to ZP cross squared union, there are just two cosets, X into ZP cross square, right? Because half the cardinality of ZP squared in ZP is just 2. Half the elements are square and half the elements are not square. So there are only two cosets of Z, right? And in an abelian group, finite abelian group, the sets of squares will be a subgroup. This is true in general. In any finite abelian group, all the squares, it will be the image of the square map from X to X squared. This is true for any group. So ZP cross is equal to this. So now, since ZP cross squared is a subgroup, the product of two squares, is a square. What about two non-squares? If U and V are non-squares, then U is equal to X into some squared, into some A squared, and V is equal to X into some B squared. They both have to belong to this coset. So this implies that UV is equal to X squared into A squared into B squared, which is in ZP cross squared. So the product of two non-squares, therefore, product of two non-squares is a square. And finally, if U is a square and V is not a square, then U is some A squared and V is some X into B squared, then UV is equal to X into A squared B squared, which belongs to X of ZP star squared. So it's not a square. Therefore, UV is not a square. So what have I shown? Product of two squares is a square. The product of two non-squares is a square. The product of a square and a non-square is not a square. So now this proves that this proves that if 0 is not equal to AB by P is equal to A by P into P by P. Incidentally, I should say that from the first, in number 1, I should say that here I can write A by P is equal to A bar by P. A bar is the remainder when you divide A by P. A is congruent because A is congruent to A bar, not P. Okay, so I have that. So this is equivalent to showing that AB by P bar is equal to A bar by P into P bar by P. Okay, but we know that the bar map, bar is, remember, RP, it's a homomorphism. This is equivalent to showing that A bar dot P, P bar by P is equal to A bar by P into P bar by P. Okay, so now I have to show that left hand side is 1 if and only if right hand side is 1. I'm assuming they are not 0. Okay, so 0 is out. So the only possible values they can have is 1 or minus 1. So I want to show that left hand side is 1 if and only if right hand side is 1. So want to show that left hand side is 1 if and only if right hand side is 1. So let us do. Left hand side is 1 is equivalent to saying that A bar dot P bar is a square. This is equivalent to saying that either A bar, B bar are both squares or both non-squares. Both non-squares. Because we saw that a square and a non-square is not a square. So either A bar and B bar are both squares or they are both non-squares. This is equivalent to saying either A bar by P and B bar by P are both 1, or both minus 1. And that is equivalent to saying that A bar by P into B bar by P is equal to 1. So left hand side is 1 if and only if right hand side is 1. Therefore, left hand side is minus 1 if and only if right hand side is minus 1. So that proves that I should also mention a remark. A dot P, if I take multiplication modulo P, this is also equal to A by P into B by P. How much time do I have left? Oh, it's almost over. Okay. So, I want you to notice this because AB is congruent to A dot PB mod P. Right? Because what's the definition of the product of A dot PB? It's nothing but the remainder when AB is divided by P. So therefore, this is nothing but AB by P. And that we have seen just now is A by P into B by P. So it's a consequence of the fact that the product of two squares is a square and the product of two non-squares is a square, but the product of a square and a non-square is not a square. So that finishes that. So next time I will do Gauss sums and the law of quadratic reciprocity. Those are the two main topics left for me, and I will do that in my third lecture. But we've got a reasonable enough introduction to the Legendre symbol. So basically, Legendre symbol is to answer the question, what are the squares mod P? What are the squares mod P? Okay. Please feel free to ask me any questions from last time, because if any of you have read, have all of you been given the notes for yesterday's lecture? Has everybody been given the notes for yesterday's lecture? Can I get an answer to that? Because I sent the notes to the coordinator. You got the notes?
No, sir.
You are, oh God, then please get them from the coordinator. I've the PDF file of yesterday's notes I've sent. Yesterday after the lecture itself, I immediately I sent it to him. So he has those notes. I don't know why he hasn't. Does he have everybody's email address? Does the coordinator have everybody's email address?
Yes, sir. Sir.
Yes, he does. Then he should send it. I don't know why he hasn't sent it. But please follow up with the coordinator that the notes for last time and today, just now I will send you the notes for today's lecture. PDF file, I will send it to the coordinator and please ask him to give them to you so that you can read them and you can question me on Monday. You have got the weekend to read them and you can ask me questions on Monday. Please ask him to distribute the notes. All he has to do is to send an email to all of you. That's all he has to do. I asked him before the lectures to make a group for all of you, a group address, email address for everybody, so that he could just in one go send all the notes. Actually, if we had made a group and given it the group address to me, I would have sent it to all of you, but he didn't do that. So in any case, he should make a group email address and send these notes to all of you. But in any case, if you have any questions, please feel free to ask me.
Good morning to all. I request the remaining attendees.
Pardon?
Please raise the questions.
What is this? What was the question? I could not understand the question. What was the question?
No questions, sir. Just
No questions. No questions. Okay.
From NRC Kakinada, no questions, sir. I'm requesting the remaining NRCs to ask if they have any questions.
I can't hear you. The voice is breaking. The voice is breaking. I can't hear you.
Sir, good morning, sir.
Yeah.
From NRC Kakinada, there are no questions, sir. I am requesting the remaining NRCs. if they-
From NRC Kakinada, I heard that. From NRC Kakinada, there were no something. After that, I couldn't hear. There were no, the people couldn't join or something. Was there some problem? It says NRC Kakinada unverified. I don't know what that means. In any case, my notes are available, so they can be given to everybody.
Morning, sir.
Yeah.
Good morning, sir. I am from NRC Karnataka, sir. Good morning, sir. Good morning, sir. Good morning.
I can't hear.
Good morning,
It
sir.
is breaking.
Sir, good morning.
Can you write it down? Is there a facility to chat facilities so you can write it down because I can't hear. The voice is breaking. And also my.
Video.
Sir, good morning, sir.
Good morning.
Sir, actually, we have irreducibility and reducibility of polynomials at a graduation level, sir.
Polynomial, you have at graduate level.
Irreducibility and reducibility of two polynomials.
The what of two polynomials? The
Not two, sir. Irreducibility of polynomials in RX, RFX. Where F is a field.
irreducibility of polynomials in Rx.
Yes, yes,
Have to
sir.
be either of degree 1 or degree 2.
So, actually, the definition is not clear. Please explain, sir, if you know.
You want the definition of irreducibility of polynomials. Okay.
Yes, sir.
Okay.
And not some examples also, sir.
Huh?
Some examples also.
Yeah, okay, okay.
Right, sir.
So, let me, okay, so irreducibility of polynomials. Irreducibility of polynomials. Okay, so f of x is said to be irreducible if whenever you write f of x as a product of two polynomials, ux into vx, then either, okay, so the non-zero, then either ux or vx must be of degree 0. Must be of degree 0. So a polynomial fx in fx, f is any field, is said to be irreducible if whenever you write it as a product of two polynomials, then one of the two polynomials must be of degree, not two, sorry. I don't know how I wrote two. It must be of degree 0. God. Degree 0. Must be of degree 0. That means it must be constant. One of them constant. And the other one will have the same degree as f. That's the only way of, if that happens, then you say that it's irreducible. So one of the properties of C is algebraically closed. Algebraically closed. This is in postgraduate, you either in a complex analysis course or in a Galois theory course, you can prove that C is algebraically closed, i.e., all irreducibles are of degree 1. Degree 1. They are the only irreducibles. So fx is said to be irreducible if it is not a unit and a constant. A unit means it's not a constant. And fx equal to this thing, then either this is. C is all the irreducibles are degree 1. Rx, using this fact, one can show that the irreducibles in Rx are of degree 1 or 2. You see, Rx is contained inside Cx, and any polynomial in Rx will factor. So if I have a polynomial a1x plus anxn, this will factor as some a1 minus x into a2 minus x, or sorry, I write it the other way around. X minus a1 into x minus a2. Sorry about that. I can write it as an into x minus some alpha 1 to x minus alpha 2 into x minus alpha n. Now, this is treating it as a polynomial on C of x, because C of x always factors like this. The irreducibles are all of degree 1. So it will factor like this. So now if I take the bar of this complex conjugate, a naught bar plus a1 bar x plus so on plus an bar xn, this would be equal to some an bar into x minus alpha 1 bar into x minus alpha 2 bar and so on into x minus alpha n bar. But if this is a polynomial in R of x, if AIs are in R, then the bars are the same. AI bar is equal to, this means that AI bar is equal to AI. So this would be just the same as f of x. This would be same as f of x. So my point is that if alpha I is a root, then alpha I bar is also a root. The whole point of this is if alpha I is a root, then alpha I bar is also a root. So, so therefore, either alpha I is real, or if alpha I is complex, then alpha I bar is also a root. So the complex roots occur in pairs. So, so suppose alpha 1 to alpha say t are real, and then alpha t plus 1 bar, etc. are the other roots, are the complex roots. So then then f of x will be some an into x minus alpha 1 into x minus alpha t into x minus alpha t plus 1 into x minus alpha t plus 1 bar, etc. They'll all be in pairs. So this will be an into x minus alpha 1 into x minus alpha t, and this product, it will be x squared minus alpha t plus alpha t bar, that is twice the real part of alpha t, plus alpha t t plus 1, alpha t plus 1 into alpha t plus 1 bar, etc. Like that. So this is in Rx. These are real numbers. So f(x) will either have these degree 1 factors or degree 2 factors. So these will be the irreducible factors. So you ask for an example. Look at this x squared plus x plus 1. X squared plus x plus 1 is an Rx. Okay, and it's irreducible. Its roots are right. This is x minus omega to x minus omega squared, and these are not real. So, right. So, if I write this as a product of ux into vx, which are real, if I write x squared plus x plus 1 as ux into vx, which are real polynomials, then the only way is that one of them is a constant and the other one is just a constant multiple of, right? The only way you can do it is like an into x squared plus a into x squared plus x plus 1 into a inverse. This is the only way you can make it up as real polynomials. So this will be irreducible in R of x, but of course in C of x it will be reducible. It will factor as x minus w into n, right? So this is an example. This is irreducible in R of x. Sorry, yeah, but reducible in C of x. So this is an example of an irreducible polynomial in R of x. So you see, a polynomial could be irreducible over a field, but it could become reducible over a larger field, as has happened in this case. And what I have proved over here is that since every polynomial can be written as a product of irreducibles, And every polynomial in R of X can be written as a product of either degree 1 or degree 2 polynomials in R of X. That means the irreducibles in R of X are either of degree 1 or degree 2. Is that clear? Any, is my explanation clear, or let me give another example. Let me give another example. Let me look at Z2X by the finite. So I have the finite field Z2 plus 2 dot 2. And let me look at the polynomial x squared plus x plus. I claim this is irreducible. Irreducible polynomial. It cannot be written. It cannot be written as a product of polynomials of degree 1. Now the point is that the thing is that if x squared plus x plus 1 is equal to x minus alpha into x minus beta, then alpha and beta have to be either 0 or 1. So the only possibility is, right, because the field only has 2 elements. Z2 has only 2 elements in it, namely 0 and 1. Right? So the only possibilities are x into x, x into x, both are 0, x into x minus 1, or x minus 1 into x, or x minus 1 into x minus 1. But this is x squared. This is x squared minus x, which is the same as x squared plus x, because plus is equal to minus 1 or 2. And this is equal to x squared minus 2x plus 1. But 2 into anything is 0, so it's x squared plus 1. So none of these is x squared plus x plus 1. So therefore, this is irreducible in Z2x. So this is an example of an irreducible polynomial over a finite field. Previous was an example of an irreducible polynomial over R. And over C, the only irreducible polynomials are degree 1. That's it. Anything else?
Thank you, sir. Thank you very much.
Yeah.
For giving an explanation.
Yeah.
Another question is there, but please send the solution of this question in our groups, WhatsApp group there. Please send it. My question is, if P is prime, x to the power n minus p is irreducible over Q.
No, I can't hear. Can you write this down? I can't hear what you're saying. Can you write this down? Or can
Sir?
you speak directly?
Sir.
Ah,
So I have another question.
yeah.
You said group, sir. My question is, if P is prime, x to the power n over Q.
No, I couldn't hear. If P is the prime and
n x to the power n minus p
x to the power of n minus p, you're looking at the polynomial
is irreducible over Q.
xn minus p, this polynomial, what I've written.
X to the power n minus p, sir,
X to the power of n minus p
is
You're-
irreducible over.
but q is not equal to p.
Yes, sir.
Is q, so you're treating this as a polynomial in zqx.
Yes, sir.
You're treating this as a polynomial in xpx, and so So P is this an irreducible polynomial? So the question is this an irreducible polynomial? Is P an nth power? Like it will depend on P and Q. Let me see. Xn minus P, treating it as a polynomial in ZQX. So let me take it. Xn. Let me try an example. Xn minus 2 as a polynomial in Z3X, say. That is Xn plus. So is 2 and nth power. Is 2 and nth power. The order of so let's see. Uh, I don't think this is so straightforward. It'll
Sir, my question is,
is this irreducible or not?
yes, sir. Irreducible
That is the question.
in Q.
Yeah, so I was trying for a special case.
Yes.
That 3 to the n.
Means rational.
I don't think it's so straightforward to be able to say whether it's irreducible or not. Straight away, I cannot think of, you see, n is anything. Whether 2, I'll have to think about this. I can't immediately think of an answer.
Okay,
If
sir.
I get the answer, maybe next time I'll tell you. But xn minus p, whether it's irreducible over q, I don't know. I immediately I can't get an answer to this.
Thank you very much, sir.
Huh?
Thank you very much for giving an excellent explanation. Thank you.
I don't think that it's easy to answer this question because
So,
it can be anything and you could break, if n is 10, you could break. How would you show that it cannot be written as a product of a degree 4 polynomial and a degree 6 polynomial. I don't think it is easy to get an answer to this question.
So, yeah, about the previous person, he asked the answer about the other state. So yes, very well.
No, I can't hear you. I can't hear you at all. It's just some, I'm not hearing you at all. You-
Sir?
On the mic, I can't hear anything at all. Ah. Ah. No, I can't hear.
Can- For
No,
giving an
it's
excellent
break.
explanation on my doubts. Thank you very much, sir. Thank you very much.
Okay, thank you.
Thank you very much. Thank you very much, sir.
Please distribute my notes to all the students.
Okay, sir.
Please distribute.
Okay, sir. Thank you.
Thank you.
In the sessions. Any questions from remaining? Please respond. Now the next session will be handled by the resource persons, key resource persons, offline session. Thank you.
లంచ్ వస్తాను మీకు చేద్దాం ఇప్పుడు తీసాను
Hello, am I audible?
Yes, sir.
Okay. Sir, but now.
Good afternoon, sir. Am I audible,
Yeah,
sir?
good. Yeah, you are audible.
Sir, welcome to the second session, sir.
Yeah,
Sir, you can continue, sir.
yeah. Fine.
Thank you, sir.
Is the screen visible?
Visible, sir.
Okay. By the way, before I begin this lecture, do you have any questions regarding the last lecture? If you have any, you can clarify those things and then proceed for this lecture. Okay, so I'll continue with this. Well, today we will discuss uniform convergence. Okay. In the last lecture, we discussed uniform continuity, and today we are going to discuss uniform convergence. And we have a common word, uniform, in the titles of both the lectures. So let's try to distinguish that uniform with this uniform. Okay. In the uniform continuity, for given epsilon, there exists delta positive independent of the location. Okay. Independent of x. That is, one delta exists uniformly for all x. Say uniformly for all x. Okay. So that was the meaning that that was the interpretation I gave for the word uniform in the last lecture. And here let us see what is the interpretation that give. Thank you. Yeah. So today let us see what is the interpretation that we are going to give for the word uniform convergence in the context of convergence of sequence of functions. Okay. Let J be an interval as in the last lecture. Okay. It could be semi-open or semi-closed or open, closed. You know, yeah. Well, let us assume that you have a sequence of functions for n belongs to n. So let us assume that you have a sequence of functions, okay, Fn j to r, be a sequence of functions. Now I want to talk about convergence of Fn, okay, objective is we want to define the notion of convergence of this sequence of functions. Okay, all right, so that is our objective. Right, see, I already told you in the last lecture, it is better we spend more time on definitions than spending time on theorems and proofs. Okay, because once we give sufficient motivation for definitions, then proofs come automatically. That's not a big deal. Okay, just fixing the details is not a great deal. Okay, well, how do we give notion of convergence of sequence of functions? We have notion of convergence of sequence of numbers, real numbers, and we have to extend the notion of convergence of real number to the notion of convergence of functions. That's it. Okay, so how do we do it is a question. One way is attach a number to function and say that when those numbers converge, then you can say that these functions also converge. That is one crude approach, naive approach. Okay, and when you give some notion of convergence to the sequence of functions, and already you know how to you have some predetermined concepts associated to the function, like limit of a function as extends to a, or maybe continuity of function, or maybe differentiability of function, integrability of functions. So these notions should behave well with respect to the convergence that you are going to, you know, attribute to the sequence of functions. Okay, so this is the most important feature. So you have to define a notion of convergence in such a way that the three things that we have already discussed in the earlier semesters, like what are the three concepts that we have studied in BSc, or that we teach in BSc related to functions? Limits and continuity in calculus, concept 1, and concept 2 is derivative, and concept 3 integrability. Okay, integral. So we define convergence of sequence of functions such that the convergence of sequence of functions in some sense respect these three predefined notions. Okay, right. So this is our objective. Okay, now one very naive approach of defining notion of convergence of sequence of functions, especially if it is real valued functions, that is just borrow the notion of convergence of real numbers. Okay, approach 1 is borrow the definition of convergence from R. Okay. So what is the definition of convergence of sequence in R? We say that AN is a convergent sequence, if the following thing should happen. What is it? There exists a limit in R with the following property. What is the property? For every epsilon, there should exist a stage n naught. Now you see, there are many quantifiers coming and you have to think of order. So this, wait, you need to be very careful about order of quantifiers. For every epsilon, there exists n naught. See, this there exists L came first. That means L is independent of epsilon and L is independent of n naught. Okay, no matter what epsilon you choose, what n naught you choose, okay, L is independent of that. Okay, okay. So whatever epsilon you choose, this there exists comes after this epsilon. That means this n naught depends on epsilon. That's what it means by I write epsilon first and then n naught later. Okay, n naught depends on epsilon such that an minus L is less than epsilon. That's it. This is a standard thing that of course this happens for every n greater than or equal to n naught. All right. So this is a standard thing. I don't want to spend more time on this. Okay. So I straight away borrow this definition and then talk about convergence of sequence of functions fn. See, for fn is a real valued function. If I fix x in J, what is fn of x? Fn of x is a real number. If I fix n and x, fn of x is a real number, right? I fix x, okay, and then consider fn of x. Okay, so this is a sequence. Okay, this is a sequence in R, obviously. Okay, I can consider convergence of this sequence, right? If I consider convergence of this sequence, and let us assume that the sequence converges, and the limit obviously depends on x, isn't it? Because I fix x, then I get a sequence fn of x. If I change x, then I might get a different sequence. Okay, it might have a different limit. We don't know. Therefore, the limit of this sequence, suppose this fn of x, okay, converges to some limit. Obviously, that limit depends on x. Converges to a number, a limit, say f of x. It is just to say that I should have written L of x. There's nothing wrong in it. Okay. because I'm using notation L for limit, right? One can straight away use the notation L of x. Okay, suppose Fn of x converges to limit, let's say L of x. But most of the textbooks write Fn of x converges to f of x. That is a standard notation. We'll quickly switch to that notation, but for a moment, let me write L of x. Okay. In next 5 minutes, I'll change this L of x to f of x. Okay. This L is a function from where to where? This L, it depends on x, right? This L is also a function from j to r. The limit, you fix any x in j, then you have a limit L. Okay. So say L here, L is a function from j to r. All right. Okay. Right. This is one notion of convergence of sequence of functions. Okay. Suppose this happens, then okay, if such a thing happens, then we say that Fn converges to L pointwise. What do I mean by pointwise? If I fix a point in J, then Fn of x is a sequence of real numbers that converges to L. Okay, now I see why we should not use the notation L to denote the limit for sequence of functions. Why? It's because usually you reserve the notation L for real numbers. When I say Fn converges to L, you will be tempted to think that this L is a constant function. L is a fixed number like 2 or root 7, which doesn't change with x, but actually it changes with x. So that's why in order to avoid this confusion, in order to have a uniform, means in order to have a consistent notation, people use f of x to denote the limit. Okay, so that we can say that Fn converges to f. Yeah. See, actually, textbooks really don't care about explaining all these details, because if a textbook author writes all these details, and each book will be 800 pages, and students are scared to touch such kind of books. So that's why people try to write things uh, in a crispy manner. Okay. So I mean, we have to supply these kind of details to students, why we are having this kind of definitions and so on. Textbook simply starts with definition 1. Fn is said to converge uniformly. This Fn said to converge pointwise if blah 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 happens. Okay, the definition should come naturally. Okay, so the theorems. It's not that somebody gives the definition, we work with the definition. No, mathematics is not developed in that way. Okay, all the definitions in mathematics come with a purpose. Okay, if we can convey this to students, half of our job is done. If students can find out the actual reasoning behind how certain notions have come up. Okay, so this is the definition of This is the definition of pointwise convergence. Okay. What do I mean by pointwise convergence? For every fixed x, okay, there should be a limit for the sequence fn of x. Okay. Then we say that fn of x, fn converges to f pointwise. Okay. Okay. So maybe I'll just okay. So fn converges to, maybe I'll write pointwise here. All right. Yeah. Let's look at some examples. Easy examples. Okay. Let fn is a function from 0 1 to r, x going to x power n. This is a very standard example in sequence of functions. Okay. Let us check whether let us see what happens to this sequence of functions, whether it converges pointwise or not. So what is that we need to do? Check whether fn converges pointwise. Okay. If so, what is the limit? Okay. What is the limit? It's an easy question to begin with. So what is that I need to do? I have to fix x in the closed interval 0 1 and just consider this sequence x power n. That's it. Okay. So what about this x power n? X power n, we already know that. Okay. Recall the sequence. Okay. Sequence x power n converges to 0 if mod x less than 1, strictly less than 1. Okay. This information we know. Okay. And then when x equal to 1, this x power n converges to simply 1 power n. It's a constant sequence. It converges to 1. When x equal to minus 1, this minus 1 power n, it does not converge, right? This is a very standard thing. So therefore, what do you conclude? Then this x power n converges to 0 if x is in closed 0 open 1, and x power n converges to 1 if x is equal to 1. It's a trivial thing. So therefore fn converges to f given fn converges to f, where what is f of x? For every x, the limit is f of x, right? What is the limit? Limit is 0 when x is closed 0 open 1, and limit is 1 when x equal to 1. That's it. This is a limit. Okay. So if you draw a picture, how does it look like? Okay, maybe lines. I'll draw lines. Okay. So after that, oh my God, it's not going. Okay. So I use stroke here. Okay. All right. So this is x-axis. This is x-axis. This is y-axis. So what is the first one? When n equal to 1, what is it? When n equal to 1, it is simply y equal to x line. Okay. And when n equal to 2, so what is it? This is y equal to x, no? This is y equal to x. This point is 1 comma 1. And of course, this is 0 comma 0 origin. So when x, this is when, maybe I should say f1 of x, not not this. This is f1 of x. F1 of x is x. Now what about f2 of x? It is x square. It is some kind of parabola. F2, that is equal to x square. Now f3 is what? It's a cubic curve which is like this. Okay, x power 4 is like this, and so on, right? As n becomes larger and larger, we have already seen that no matter what is our x, suppose this is our let's say x naught. Okay, as n goes to infinity, what happens? X naught power n becomes closer and closer to 0. So like this, this sequence will be like this. All right. So what is the limit, by the way? Limiting function, okay, is actually 1. Sorry, it is actually 0 till x is less than 1. The moment x is 1, the limiting function takes the value 1. Okay, so this is the one. So maybe let me draw limiting function separately. Okay. Okay, so this is no. Okay, so the limiting function is this. Oh my God, no, not this one. I will add one more. Okay, I'll use some other color. Okay, this color let me use. So the limiting function is this 0 up to something, and after that it is 1. Okay. So clearly the limiting function are okay. Clearly f is discontinuous. Oh God. So you have a discontinuous limit. So what did we do? We proved that pointwise limit of continuous functions need not be continuous. Okay, This is the first observation. So as far as the first one is concerned, first operation of functions, what is it? Limit. This limit is gone. When you adapt simply this convergent notion of convergence from real lines and say that sequence of functions is convergent if you fix x and the corresponding fn of x, that sequence converges to the limit, then though if the sequence has good property, that is every element of that sequence is continuous. Okay, every element of the sequence fn, namely fn of x equal x power n, is continuous, but that beautiful property is lost when you pass to the limit. What is that limit? F of x equal to this pointwise limit. So pointwise limit, it actually doesn't preserve continuity. So this is a bad this thing. So if it doesn't preserve continuity, you don't expect that it preserves differentiability also. And what is an example? Same example. Each fn is differentiable, but the limit is not even continuous. So therefore, if the function is therefore the function is, the limit is not differentiable, because every differentiable function must be continuous, no, to begin with. The function itself is it is discontinuous, and there's no point in checking differentiability, because obviously it is not differentiable. Okay, and then let us look at integrability, pointwise limit and integrability. Let us look at the third one. Okay, so as an immediate corollary of this, what you can say is, you can simply say that okay, so let me see whether I can, no, this is not like that. Okay, okay, I say insert. Oh, sorry. Okay, this is okay. No, this is not working. Okay, so pointwise limit of differentiable functions need not be differentiable. From the same example, okay, each fn is okay, but each fn is differentiable. Okay, so these two things are there, and let me look at example number 2. Example number 2 is okay, you just start with e power minus nx square. Okay, and then you just differentiate this. If I differentiate this, what do you have? So you have minus nx, maybe 2nx, e power minus nx square. Okay, and then I integrate this. Integral 0 to 1, derivative of e power minus nx square dx. So what is it? What is it? This is e power minus nx square 0 1. Yeah, maybe I put plus here and then minus here, and then I put minus here. Yeah, I'm in class. So e power minus n. Okay, 1 minus e power minus n. Okay, so what is this? As n goes to infinity, this goes to 1 as n goes to infinity. Okay, now let us look at the situation. Okay, so this is a simple observation. I just want a function whose integral is 1, whose integral tends to 1. That's just that is just a simple thing with which I started. And then now consider what is this actually. This is integral 2nx e power minus nx square, right? Okay, now consider fn of x is equal to 2nx e power minus nx square. Okay, where x is in 0 to 1. Okay, now what happens as I fix x in 0 1. Okay, fix this and then consider this sequence. What happens as n tends to infinity? Consider the sequence. And what happens as n tends to infinity? Think about it carefully. As n goes to infinity, you have n. Okay, as n goes to infinity, 2nx is actually tending to infinity, but you have e power minus nx square. So e power minus n is actually becoming tending to 0. 2n is tending to infinity. So what about the product? Where is it going as n tends to infinity? As n tends to infinity, what do you have? 2nx by e power nx square. What happens? Limit n tends to infinity. Okay, think of it. If you want, you can just violate some rules and then consider n as a continuous variable instead of discrete variable, and then you can use this is infinity by infinity form. You can use L'Hopital rule. Okay, if you use L'Hopital rule, what happens? Okay, maybe you L hospital is a bad pronunciation of this thing. Okay, of this French mathematician's name. It's not hospital, it is hopital. H, you keep H as silent. Okay, L-O-P-I-T-A-L, Lopita. Okay, don't pronounce this as L hospital or maybe some hospital. There's no hospital. Okay, his name is Opita. So if you use Lopita with n as an independent variable, so it is like 2x by x square into e power nx square. Okay, if you differentiate with respect to n, and then now let limit n tends to infinity. So what happens? This is 0. So this goes to 0 as n goes to infinity. Okay, no matter what is your x could be 0, doesn't matter, or x could be 1. Okay, so what is that we have observed? Integral fn, okay, integral 0 to 1, this is actually equal to, what is it, 1 minus e power minus n, which converges to 0 as n goes to infinity. But what about its limit? What about its limit? What is fn of x? Okay, so here fn converges to f pointwise, where, okay, I write the p dot w dot to denote pointwise convergence. Okay, p dot w dot means pointwise, where f is identically 0. Okay, so fn converges, integral fn from 0 to 1. Oh, sorry, this actually converges to 1, right? It actually converges to 1. Oh my god, this is okay, but the limit, but integral 0 to 1 f dx, this is actually 0 function, right? It converges to this. So what is that you have? Okay, hence integral fn converges to 1, but integral f equal to 0. So what you have is fn converges to f pointwise, but integral fn does not converge to integral f. Okay, this is 0 to 1, this is 0 to 1. Why? Because integral fn actually converging to where? It is converging to 1, but integral f is 0. Okay, this limit is actually tending to, this tends to 1, but this guy is actually 0. Okay, so pointwise convergence doesn't respect integration, roughly speaking. Okay, so you have pointwise convergent sequence, but limits are behaving crankily. Okay, so all the three operations that we have started, they go wrong if you simply adopt pointwise convergence. Okay, that is from these two examples. Fn converges to f pointwise. Each fn is continuous, but the limit need not be continuous. Fn converges to f pointwise. Each fn is differentiable, but limit is not differentiable. Need not be differentiable. Sometimes it could be differentiable, sometimes it need not be differentiable. Fn converges to f pointwise. Fn, each fn is is integrable, but integral fn's may be different. By the way, that motivates me to give another example. This is a beautiful one. This is in principle it's one of my favorite examples at BSc level. Okay, objective is to construct a sequence fn such that number one, each fn is Riemann integrable, and number two, fn converges to f pointwise. Number three, if I have to argue against pointwise convergence, what should I do? Like earlier I have shown, no, each fn is continuous but f is not continuous. Similarly, I should say that each fn is Riemann integrable but f is not Riemann integrable. Okay, so this is a very easy construction once you understand what is pointwise convergence. Of course, you might think that the title of my lecture is uniform convergence, but I have not yet arrived at the definition of uniform convergence. As I told you that better give enough motivation, give enough, create enough hype for the actual, notion, so that the importance of the concept actually it will be appreciated by the students. Okay, so this f is not okay. Example is quite easy. All that you need to do is start with the non-Riemann integrable function. Okay, start with a function which is not Riemann integrable. What is the standard example that you see that is not Riemann integrable in textbooks? That is a characteristic function of rationals. That is, if x is rational, you keep it as 1. If x is irrational, you define the function to be uh, 0. Okay, so it is 1 if x is in 0 1 intersection q. It is 0 if x belongs to, if x is any other function, sorry, if x is any other number in 0 1 which is not a rational number. Okay, start with this f. Now all that I need to do is I have to construct a sequence of functions which converge to this such that each function is Riemann integrable. I know that functions are Riemann integrable if they have only finite number of discontinuities. Okay, so what I do is I write, okay, so what is it? Let first arrange all the rational numbers in 0 1 in the form of a sequence. Let q intersection 0 1 be like this. Rn where n belongs to n. They are all countable, so therefore I can actually arrange them in a sequence, R1, R2, R3 and so on. Okay, they are all rational numbers. So all rational numbers are in this set, are in the form Rn. Okay, and then you define Sn to be maybe S capital N. What are they? So it's like R1, R2, like R capital N. That means first capital N rational numbers here. Okay, Sn is like this. Okay, now what about Fn of x? Fn of x, it is equal to 1 if x belongs to S in S capital N. 0 otherwise. Okay, so 0 if x belongs to closed interval 0 1 minus Sn. You can check clearly. Now it's a trivial exercise for students that you can give. Okay, or you yourself can give the proof in the class if you want. A trivial exercise would be show that this Fn converges to F pointwise. Okay, I'll give you a quick oral proof. If x is an irrational number, then each Fn of x is 0. Okay, therefore it's a constant sequence 0 converging to 0 if x is irrational. Okay, that is done. If x is a rational number, then that x will be in S capital N for every n greater than or equal to n naught. Okay, if x is rational, then okay, this x will be in one of these sets, right? R1, R2, x will appear in this sequence. Then there exists n naught such that x belongs to Sn for every n greater than or equal to n naught. Why? Because this set Sn is increasing, right? It is becoming bigger and bigger. S1 is a subset of S2, is a subset of S3, and so on. If it is in one of the Sn naughts, Sns, then it will be in all Sms greater than where m greater than Sn. Sorry, m greater than n. Okay. So because no, these sets are this is increasing. S1 is a subset of S2, is a subset of S3, and so on. Okay, S2 is a subset of S3, and so on. So it will be certainly in Sn naught for some n naught. Therefore, it will be in all Sn for every n greater than or equal to n naught. So therefore, Fn of x, it will be 1 after certain stage. Therefore, the limit is 1 when x is rational number. So therefore, that is precisely this one, f. Okay, and observe that each Fn is Riemann integrable. Why? Because the points of discontinuity of Sn, they are precisely the points which are in Sn. Okay, at all other at all other points except the finite number of points which are in Sn, function is 0. Okay, so therefore the points of discontinuity of Fn are precisely Sn. Okay, because the points of discontinuity of Fn is the set of points of the set of points of discontinuity of Fn is Sn. It's a finite set. Therefore, every function which is continuous except a finite set is Riemann integrable. That theorem you would have proved in your Riemann integration course for students. Okay. So what did we prove? We obtained a function, a sequence of functions, namely this, such that each function is Riemann integrable, Fn converges to F pointwise, and the limiting function is not Riemann integrable. Therefore, pointwise thing, it does not actually respect Riemann integrability also. So all three things are gone. So what is the way out? The way out is don't take these limits. What is it? The definition of convergence of numbers from R straight away, but you look at the geometry. What is the geometry of this thing, and then take help from geometry of convergence of sequence of functions. This is approach 2. Approach 1 gave some kind of convergence which is not so useful. Okay. Approach 2. Okay. Get geometric interpretation, or maybe use, not get, use geometric interpretation. Okay. Geometry might help you. Interpretation of convergent sequences. Okay. Of convergent sequences in R. That is, what is the geometric interpretation? So I say that Xn converges to L if the following thing happens. You take L, okay? You take any epsilon, and depending upon epsilon, there exists N naught, okay? There exists N naught natural number such that what happens? All the terms of the sequence, they are in this interval, L minus epsilon to L plus epsilon. They are all here. Okay. Xn minus L less than epsilon for every n greater than or equal to n naught means what? Everybody is in between L minus epsilon to L plus epsilon. Okay. So they are all here. All right. Now we'll take this as a motivation and then give definition of convergence of sequence of functions. Okay. Now you have Fn. Consider Fn's from J to R. Okay. And you have a function f in your hand. F is also from J to R. Okay. They should have a common domain. Then only you can, it makes sense, no? Fn converges to F. Okay. Okay. Then what is that you need to do? I take this, I draw a picture now. Oh, no. I draw axis. Okay. Okay. Yeah. Suppose your F is like this. Now, this is very thick. I want something which is like this. Okay, so this is F. Okay. Now I want to, this is limit, right? Around L, what did I do? What did I take earlier? I took an interval. Now around F, what do I mean by taking an interval? I actually take an epsilon band. Okay, an epsilon band here. Okay, so what do I mean by epsilon band? It is like this. I just trace this. Okay, it is just the same f with translation. So this is what? F plus epsilon. This is f minus epsilon. That's it. Like this was L plus epsilon. It was L minus epsilon. In the same way, you draw f plus epsilon and f minus epsilon. Earlier, what did you say? You said in the case of real numbers, what did we say? We said all the numbers in the sequence, all the elements of the sequence, sorry, all the terms of the sequence, they are between L minus epsilon and L plus epsilon, right? Here also we should say the same thing. After certain stage, for every epsilon, there exists an n naught. Okay, so we say that Fn converges to F. Okay, if for every epsilon there exists n naught, I intentionally left some gap here. I want to write something here. That's why I left a gap here. For every epsilon positive, there exists an n naught such that what should happen? All the functions, when you draw the when you draw their graph, okay. No. Here I'll use another. When you draw their graph, they'll be here in this band. Oh, why did they vanish? Okay. So F5 means Fn naught plus 2. I don't know why they're suddenly vanishing. Okay. So they are like this. So what should happen here? There exists n naught such that Fn of x is actually between which 2 points? If you fix x here, this is f of x minus epsilon. The one which is above is f of x plus epsilon. Okay, maybe I'll draw a line like this, straight line like that. Oh, no, not here. No, just a minute. What is this? This straight line is not working properly. Okay. Okay, let's assume that it's a straight line, though it is bit bent here. Okay, so maybe let me draw carefully. Okay, so this is f of x minus epsilon. This is f of x plus epsilon for this x. Huh? So this all fn naught, all fn of x's are between f of x minus epsilon and f of x plus epsilon. Okay, so it is actually, what is the meaning of it? This is less than epsilon, and it happens for every x. Okay, now observe carefully, this n naught, it depends only on epsilon, not on x. You understand? So this n naught is independent of x, or You see, this n naught is uniform for every x. Okay, so that's why you say that it converges uniformly. See here, whereas in the pointwise definition, what did you what did we demand? We demanded that fn of x should converge to f of x. What is the meaning of fn of x converging to f of x? If you write in terms of epsilons and deltas, sorry, epsilon and n, let me create a space and then write here. Yeah, so what do you have here? This fn of x converges to a limit, right? So that means for every x in J, okay, for every epsilon positive, there exists n naught such that fn of x minus f of x is less than epsilon for every n greater than or equal to n naught. Of course, here I would have forgotten. Where is, did I write n greater than or equal? Oh, maybe I should write n greater than or equal to n naught. For every n greater than or equal to n naught. After n naught stage, everything is here. Now you see, here again you look at the order of quantifiers. This n naught, this depends on both x as well as epsilon. This n naught depends on x. So this n naught is not uniform for every x. If x changes, then n naught also changes. Therefore, this is not uniform. Okay. If this n naught is independent of x, then you say that the convergence is uniform. So this is the importance of the word uniform. Okay. So what is uniform? N naught is uniform. It is independent of what? Location x. Okay. So this is the definition of uniform convergence. Okay. So I took nearly 1 hour to actually give you the definition of uniform convergence. If you straight away, go to correct, land up at a correct definition, maybe sometimes you may not know in other instances what to do if you land up in a wrong place. So maybe it's a good idea to explore things instead of straight away using Google Map kind of thing and landing at the right place. It is better to hover around and explore the other possibilities, at least in science. Okay, and therefore once you have this, we'll ask the same old questions. Recall the old questions about the behavior. So with respect to limit, continuity, differentiability, and integrability. Okay, and integration. We ask the same questions. Okay, and it turns out to be, since he is the right candidate, answers for most of the questions are yes. Theorem 1. If if fn is a function from J to R, okay, and of course f is also a function from J to R, and fn converges to f uniformly, okay, then what happens? then every point of, okay, no, wait. Okay, let x belongs to J be the point of continuity of all fn's. That means at x, every function is continuous. Okay, every function in this sequence is continuous. Then f is continuous at x. Okay, so what did we state here? If there is a point at which all fn's are continuous, then the limit also should be continuous at that point. Okay, so this is an excellent result as far as continuity is concerned. Okay, for instance, if fn is continuous everywhere, okay, if you have a sequence of continuous functions, then obviously from this result what follows? F is a continuous function. Okay, because fn is continuous at every point of J for every n, then the uniform limit f is continuous at every point. Okay, so and proof is quite simple. All that you need to do is, in order to prove continuity of at x, all that you need to do is you need to estimate this. For given epsilon, you have to find the delta such that this can be made less than epsilon whenever x minus y is less than delta, right? So a trick, I'll tell you, a very standard trick which will be used throughout your discussion on uniform convergence, is this adding and subtracting. Okay, fn of y. Okay, maybe I add this. No, wait. Control. Okay, so you add and subtract this fn of x minus fn of y plus fn of y minus f of y. Okay, and you write it like this: fn of f of x minus fn of x okay, plus fn of x minus fn of y plus fn of y minus f. Just a triangle inequality, nothing else. Okay, now we observe carefully. Fn converges to f uniformly. Therefore, after certain stage, after sufficiently large n naught, this can be made less than epsilon by 3, and this can be made less than epsilon by 3. Okay, and for that sufficiently large n naught, okay, fn naught is continuous at x. So therefore, the delta that works for fn naught with epsilon by 3 is something that works for f. That's it. That's the end of the proof. Okay, if you understand this carefully, it is just one line proof. And what's the byproduct of it? I can write the same thing in a different way, in a very beautiful manner. So that is So what is limit y tends to x, fn of y? If f is continuous at x, sorry, if fn is continuous at x, so this is fn of x, right? Isn't it? If fn is continuous at x. Okay, this is a trivial thing. Okay, suppose you have a, okay, suppose the my basic assumption is x is in such a way that each fn is continuous, right? All right. Now what about limit n tends to infinity, limit y tends to x, fn of y. Up to this part, what is it? Fn of x, right? What is limit n tends to infinity, fn of x? That is f of x. By the way, I should have given a remark here. I should have given a remark here. The trivial remark here is if fn converges to f uniformly, then fn converges to f pointwise. It's a very trivial remark. Okay, you can just check this. Exercise is visualize this geometrically. Visualize it geometrically. Okay, so this is f of x. Oh, no. So this is actually limit n tends to infinity, fn of x. Right? That's, oh, sorry, that's what I have started with, no? Okay, maybe I'll use stroke eraser. Okay. Yeah. Now suppose if I interchange the limits, what do I get? So this is y. Suppose I take limit y tends to x, limit n tends to infinity, fn of y. So what is it? This is actually limit y tends to x, limit n tends to infinity, fn of y is what? It is actually f of y. Okay. And what is the theorem that I just proved? I said that if x is a point of continuity of all fn's, then x is a point of continuity of f also. If x is a point of continuity of f, then what about limit x tends to limit y tends to infinity? Sorry, limit y tends to x f of y. That is f of x. Okay. So you see, same right hand sides. So therefore, these two things are same. You have this beautiful relation. What is the beautiful relation I have? Let me write them. Limit y tends to x and limit n tends to infinity, fn of y is equal to limit y tends to x here, limit n tends to infinity, fn of y. Okay, so this is a consequence of uniform convergence. Okay, this is how limits and continuity are respected with respect to are respected in the notion of uniform convergence. Okay, so next thing is integration. Okay, so if each fn from maybe I take closed interval AB to R is Riemann integrable. Okay, okay, there is a notation, no, RAB. I'm sure you must be using. RAB means Riemann integral function of function which is Riemann integral and closed interval AB. Okay, if each Fn is in RAB and Fn converges to F uniformly, then F is also a function of F is also a function which is Riemann integrable. Okay, moreover, in fact you have this integral of this converges to integral a to b f of x dx. Okay, and of course if I have to write this in a different way, so what is this number? This number integral a to b f of x dx, it is a limit of what? This sequence, right? Limit n tends to infinity integral a to b fn of x dx. Okay, so this and this, these are same. Okay, I have just rewritten in a different way, that's it. But this is equivalently, what is it? Integral a to b. What is f of x? F of x is limit n tends to infinity fn of x dx. Okay, so this is equal to limit n tends to infinity fn of x dx. Okay, so here what did I do? I have actually took the limit outside of the integral. Okay, earlier it was inside, now I took outside. So interchange of limit and integral. Earlier interchange of two limits. Okay, this is theorem 2. Proof is identically same, no difference at all. If you have to show that f is Riemann integrable, what is that you need to do? Just show that Riemann sum, consider the Riemann sum and show that uh, it converges to appropriate limit. Okay, and in fact here you can show that this Riemann sum is a Cauchy. It's a Cauchy sequence on the left hand side. Okay, and the strategy is same, just add and subtract. Consider a Riemann sum for f and then add and subtract appropriate Riemann sums of fn. Use that fn is Riemann integrable and then conclude that f is Riemann integrable. That's it. No, philosophically there is no difference between proof of theorem 1 and proof of theorem 2. Just supplying of details will vary, that's it. Okay, and most important remark here where people make mistake is like a parrot, people try to by heart that if Fn converges to F uniformly, then integral and limit can be interchanged. Answer is no. You should not do it. Okay. Suppose Fn of x is equal to 1 by n. Okay. For every, let's say x belongs to 0 to infinity. Okay. Then Fn converges to 0 uniformly. You can check that. How do I know this? It's just, they are straight lines, right? F1 is 1, F2 is 1 by 2, F3 is 1 by 3, and so on. So what is the limit? For limit, I guess that pointwise limit is 0. I compute that pointwise limit is 0. And around 0, what is that you need to do? You have to consider a strip, epsilon strip. After certain stage, all the functions are in this epsilon strip. Okay, so they are all in this strip. So therefore, Fn converges to 0 uniformly. This is how you conclude. But what about Fn? But integral over 0 to infinity Fn, it does not converge to integral over 0 infinity Fn. This is actually infinity. This does not converge to 0. Okay. Earlier result makes sense only for compact intervals. Remember that this makes sense only for compact intervals. It's not for improper Riemann integration. It is only for usual Riemann integration. Okay. I conclude this with final remark. The final remark is differentiation is not respected. By uniform convergence. Okay, this is the only bad part. You need something stronger. Uniform convergence behaves well only up to continuity, but not differentiation. So remark. Okay, so there exists a sequence of differentiable functions fn's, namely, in fact, there is a sequence of polynomials itself. Okay, okay, maybe I'll just state the result due to Weierstrass. Sequence of there is a sequence of polynomials, obviously differentiable functions, such that, okay, polynomials Pn and a function f from 0, 1 to r, such that number 1, Pn converges to f uniformly. Okay, so uniform limit of continuous function, so therefore f is continuous. A function is continuous. Second is f is not differentiable at every point at every x in closed interval 0, 1. Okay, this result is due to Weierstrass. Maybe instead of calling it as a remark, let me call it as a theorem due to Weierstrass. Okay, okay, there is a sequence of polynomials. So uniform limit of infinitely many differentiable functions also need not be differentiable at any point. Okay, they can converge to a very nasty function also. So therefore, as far as differentiation is concerned, you can't say anything. Okay, and of course there are other theorems which relate uniform convergence and differentiation that I'm not going to discuss because of time constraint. Okay, So with this, I stop my lecture and questions are welcome. And I my sincere thanks to Dr. Madhavi for her efforts to organize this and for inviting me to interact with you and give these lectures.
We are very fortunate to have you here, sir. You only coordinate the public program.
Hello, I'm not able to hear. Or is there anybody who is asking a question? Hello.
Thank you, sir. We are very fortunate to have you here. And the SAR only coordinated the complete program. He advised Dr. D. Uh, Dr. D. Venkunaidu sir also for complex analysis. Thank you very much, sir. Sir, am I audible, sir?
Yeah, you are audible. Yeah, you're welcome. Are there any questions?
Yes, sir. Any questions from any analysis? So, good evening to all. I kindly request Dr. Nagasisika from JDC NRC Anantapur to extend a vote of thanks.
Dear sirs and
Yes, sir.
madams, good evening to all of you. I am M. Nagashishikala from NRC Anantapur, working as lecturer in mathematics in Government Degree College Anantapur. It's my honor and privilege to extend a heartfelt vote of thanks to Professor T. Suman Kumar for gracing us with his profound knowledge and insights on the topic of real analysis, specifically uniform convergence. Today we had the privilege to delve deep into the intricate world of real analysis under the expert guidance of Professor T. Suman Kumar sir. His ability to elucidate complex concepts with clarity and precision is truly commendable. The way he unraveled the nuances of uniform convergence, making it accessible and understandable to all, speaks volumes of his expertise in this subject. Sir, uh, passion for teaching and dedication to his field are evident in the way he engages with his audience. His enthusiasm is infectious, inspiring all of us to delve deeper into the subject and kindle a greater interest in real analysis. Moreover, Sir commitments to excellence does not stop at imparting knowledge. His encouragement, patience, and willingness to answer our queries have been invaluable in our learning journey. We are grateful for his mentorship, which extends beyond the classroom, guiding us towards a deeper understanding and appreciation of the subject. In today's fast-paced world where knowledge is ever evolving, it's rare to come across educators who are not only knowledgeable but also passionate about their subject. Sir is undeniably one such gem whose dedication to teaching and research serves as an inspiration to all of us. On behalf of everyone present here, I would like to express our sincere gratitude to Sir for his enlightening enlightening session today. Your insights, wisdom, and commitment to education have left an indelible mark on us. We are truly fortunate to have had this opportunity to learn from you. Thank you, sir, for your invaluable contribution to our academic growth. We look forward to more enlightening sessions with you in the future. Thank you all for your attention and have a wonderful evening. Thank you.
Thank you very much. Yeah.
Thank you, ma'am.
Okay.
Sir,
Okay.
especially from our Commissionerate College Education for coordinating us in this in formation of this program, sir. Thank you, sir.
Okay. See you. Bye.
Good evening, sir.
Yes, good evening.
Sir.
Actually, I cannot hear you properly.
A warm
There is an
welcome to
echo.
the sir. You can start the session.
Okay, I see. Yeah. Okay, so can you see my slide, this board? Can anybody tell me whether you can see the, okay, yeah. So let me begin with yesterday's, someone asked the question. I hope that person is here. So the question was the following. So,
Good afternoon,
yeah,
sir.
yes,
I'm here.
yes, good afternoon. Okay, okay. So you ask if every ideal is prime, right? What happened? Actually, that's the, so I guess you asked for Boolean ring, but let me show for commutative ring. So it's interesting. So suppose let A be a commutative ring. Of course, with unity, I'm always assume that it is with unity. So if every ideal is prime, then actually A is a field. Okay. Hello. Is there any question? Sorry.
Sir.
No, I cannot hear you.
Sir.
Ah,
ABA completing if every is primary and A is a field. So not this every max ideal is an ideal, prime ideal.
oh, that was a question, is it? Actually, there is a echo. Someone, can you mute rest of the people who are not speaking? Okay, so let me understand the question that every prime is maximal, is it? That's what you want.
Every prime ideal, every maximal ideal is a prime ideal.
This is true in general.
True, yes, okay, sir. Now the question is, every prime ideal is not maximal.
Yeah. No, that way I will give the example. We will
Okay,
see.
sir.
Yeah.
So another question is, in a Boolean ring,
Yeah.
every ideal is prime ideal or not?
That's what I'm saying. That so I will answer it in the way I have written. Okay. So
Yes,
I'm
sir.
saying that if you have a commutative ring, so for instance, Boolean ring is a commutative ring, right?
Yes, sir. Yes, sir.
So if every ideal is prime, then it has to be filled. So therefore, when you consider Boolean ring, it should be a filled with two elements, nothing else.
Yes.
That's the answer. So I will show this for general commutative ring. Okay.
Okay, sir.
And about the ideal which is maximal but not, sorry, prime which is not maximal, we'll see the examples. Yeah. Okay.
Okay, sir.
Yeah. So let us try this. So first of all, we have to say that, so at 0 is an ideal, 0 is always an ideal. This will imply that 0 is prime, right? And this will imply that, remember the definition of prime ideal, that if I have a two elements which are in the product of two elements in an ideal, then one of them has to be. So when we want to say 0 is a prime, this will imply that A is an integral domain. Okay, so as sir was asking about Boolean ring, actually from this you can conclude, because if you have a Boolean ring which is an integral domain, so Boolean ring means x square is equal to x, so that will tell you that x is either 0 or 1. That's the only possibility, right? But I wanted to have something more general. So okay, so suppose, okay, so because 0 is a prime, you got an integral domain. Now what you do is, so let any non-zero element you take in A, okay, and consider the ideal generated by that. By A. So, okay, so we call it, right? Our notation was ideal generated by A. So now this is prime by assumption, that is okay. Furthermore, we have you have A square ideal generated by A square, right? This is also prime. This is by assumption because every ideal is prime. Right? So what does it, yeah, what does it say? Can anyone tell me? So see, you have this is also prime. This imply that ideal A is prime, right? And A square is also prime. Then what can you conclude? Anyone can? So this will tell you that A is a unit. So A is a non-zero. Remember, we are in a domain now. So this will imply that A, right? A is a unit. So no matter which, remember, right? A square. See, A square is also prime, but A square is in A. So you can, yeah, I hope it's clear. Okay, so this will imply that this is also prime. Is it okay? Okay, so therefore, so no matter which ideal, so in this case, so this is more general. If you have commutative ring, every ideal is a prime, then there is no other option. So A has to be filled. So first of all, we showed that it is integral domain. Okay, then we showed that, well, any non-zero A is a unit. So therefore, we get the result, right? Is it clear? Is it clear that this is unit? Okay, just to make sure that, okay, so A into A, which is A square, is is in A square, of course, but it is prime. So prime means A should be in A square. So A, I write it as A square into something, let's say X. Understood? So therefore, because I am in a domain, I can do the cancellation. I can have this. So that's what A is a unit. Okay. Okay. Yeah. So before proceeding to other question that anyway I'm going to answer, but I want some other things. Namely, that's very important. If there is a time, I can prove it. But as of now, I want to give the general version of division algorithm. So general, not the most general, but yeah, sufficient general division algorithm. So that's very important, and want to use it to give some geometric example. So what is it? So again, I will concentrate on the commutative rings. Let A be a commutative ring with unity, of course, always. Okay. Now I want to consider, remember the usual division algorithm is for polynomial over field, but here I'm taking any commutative ring. Okay, in fact, this is true for general rings as well. Okay, and proof is basically same, but some care has to be taken while multiplication. Okay, we'll see that. So yeah, take this unity and suppose f and g are two polynomials given over the ring. Okay, with, let's say, the leading coefficient with the leading coefficient of G is Bm. Okay, so in particular, the degree of G is M. So this is just the assumption. Then it says that then there exist, okay, then there exist some polynomials Qx and Rx in Ax such that something like okay, uh, and some k in natural number such that I can write this polynomial fx. However, we are dealing with general ring, so this factor will come into picture. Okay, so that's the change that will happen for the general ring. Rest of it is same. Okay, where the degree of R is strictly less than degree of G. Okay, so I'm as of now I'm just stating the statement here, but if time permits I can prove it. So actually basically the proof is exactly the same as in the field case. Okay, so field case you will see that because the every element non-zero element is invertible, this factor, this is a crucial one, won't occur when you are in a field. Similarly, when your polynomial has a leading coefficient 1, G has a leading coefficient 1, then also it won't occur. And that's where we will exploit the thing. Now, what is a good thing about it? So this is for any commutative ring and the polynomial ring over that, right? So remember from yesterday, we talked about polynomial ring in two variables, right? That I can, the very construction, the way I have given was, if Rxy, then it is Rx, right? You can take A to be Rx and Y to be the variable. Okay, so we will see. Okay, so before that, again, I want another notion of the quotient. So quotient ring. So quickly, I will simply, I'm sure that you have seen this, but just to, okay. So again, let A be commutative. A be commutative ring, of course, with unity, and let I be an ideal of A. Okay, ideal of A. Then we define equivalence relation. So A is related to B if and only if A is congruent. Okay, we'll write that afterwards. A minus B belongs to I. Okay, this is the relation. What is it? This is ideal. We are saying that two elements of where, of course, A and B are part of A. There are two elements, okay, which are related. I've declared it. This is definition. If their difference belongs to ideal I. Now note that this is if and only if B minus A also in I, because I is ideal, so I can multiply by minus 1. Remember, minus 1 is there. I multiply and you get the same result, right? So if and only if this way. Actually, you have seen it, okay? You have seen it, namely while constructing Z mod NZ remainder, exactly the same thing, but generalization. Okay, so first thing to note is that this is an equivalence relation. Okay, very easy to show. So I will leave it to you. The equivalence classes, the equivalence classes, the set, okay, the set of equivalence classes is denoted by A mod I. That's the quotient ring. In fact, if A belongs to A, the equivalence class of A will be denoted by AI. Okay. Okay. Furthermore, now we want to make this as a ring. It is not just a set, but it is a ring. You define the addition. So I have two equivalence classes and I have another this A and B. So I will define this plus. This is the definition. Well, simply you add them in the ring and take the equivalence class. Similarly, if I have this into this, I will define it as first take the product in the ring and then take the equivalence class. Okay, that's how the quotient is defined. So this is a quotient ring. Okay, so now with that I want to have the important result. Let's call it proposition is the following. Again, let A be a commutative ring with unity. Okay, then this thing, the M is a maximal ideal of A if and only if. So okay, I should rephrase, but anyway, if and only if A mod M. So M so I should write more carefully. Let M be an ideal of A. Okay, then M is a maximal if and only if this is a field. Okay, and secondly, let P be an ideal of A. Then we will see when it is a prime. So P is a prime ideal of A if and only if A mod P is an integral domain. Okay, right? Have you seen this? Okay, so again we can come back to the proof afterwards, but let us I want to do some examples using these things. Okay, so let the following happen. Okay, all right, so we will come back to proof afterwards. Okay, so let's take example. Okay, so I want to take, so let no so consider, let's say consider a ring x comma y. Okay, and and okay, actually that also I have to write. So before example also I have already defined ring homomorphism yesterday, but let me define. There are a couple of things. So definition of ring isomorphism. So for that, just to define it, so let A comma B be commutative rings with unity. Okay, a ring homomorphism phi from A to B is said to be ring isomorphism if there exists a ring homomorphism psi from B to A, okay, the opposite one, such that the corresponding compositions are identity on B, and psi composed with phi is identity on A. Okay, so ring homomorphism. So basically A and B are given. You already have phi. So now you require, what is require is psi. Okay, such that if I go via psi first, then apply phi, I should get identity. If I go to phi and then apply psi, I should get identity. Okay, that's what I've written. So this is a ring homomorphism where the composition in both direction is identity. Okay, so this is the definition. Another one, which is another result, but I think lack of time I cannot do it, but important result. So called isomorphism. Isomorphism theorem. So what is it? So first of all, let again A comma B be commutative rings with unity. Commutative rings with unity, and let phi from A to B be a ring homomorphism. Okay, consider ring homomorphism. Then first of all, we define the kernel. So kernel of phi, this is by the definition, collection of all elements of A domain such that phi of A is 0. 0 is the additive identity in B. Okay, then this kernel is an ideal of A. It's very easy to see because even we can check even now. If A and B are there, remember, because of homomorphism, ring homomorphism is a group homomorphism. If A and B maps to 0, then so is phi of A plus B, right? Because phi of A plus B is phi of A plus phi of B. Similarly, for A into B, just follows from the ring homomorphism definition. So this is an ideal. Okay, then, and the image of phi, what is the image? By the definition, it is phi of A belongs to B such that A can be any element of A is a subring of B. Now remember again that we have rings with unity. Not only that, we are saying that if I have a ring homomorphism, it should map the unity of A to unity of B. So our subring has a unity. Okay, that is another thing that you should uh, see while reading other books. So some of the books may not require a subring with unity. Okay, so this is that. So you itself a ring. Then this is happen. Furthermore, the main thing that now you can, because the kernel is ideal, I can take the quotient kernel phi. Now this fellow is isomorphic to the image. Okay, so this is isomorphism theorem. That's very important. Again, I don't think we have time, but I will assume this. That's very important result. Okay, any question as of now? Okay, so let me give example. So we'll use everything whatever I have written above to give examples, because the examples are actually coming from geometry. I will show you how. So consider, okay, consider, let's say, first of all, let's say consider Rx to be ring, okay, A to be this, and consider X to be ideal, okay, ideal generated. Actually, yesterday we showed this. It is a prime ideal. So let me show it in different way. So what I will do is that, okay, so claim is that I will show this P is in fact ideal generated by X is a maximal ideal as well. Okay, what I'm going to use, I'm going to use the isomorphism theorem and the criteria that we have seen. Maximal ideal if and only if the quotient is a field. So how to show? So for that, consider the evaluation homomorphism at 0. So this is from Rx to R. What is the map? If I have a polynomial x to the power I, so 0 to n, let's say, where will it go? I want to substitute instead of x 0, so it will go only to a0. That's it. Okay, evaluation at 0. Right now, yesterday we saw that this is a ring homomorphism. We have seen for any ring evaluation, right? Of matlab polynomial ring. This is a ring homomorphism. Okay, this is a ring homomorphism. So that is okay. And note that what is the image? I can have a constant polynomial, for instance. For instance, if I have a, if I have, let's say 2, where will it go? 2 will go to 2. That's it. I have, let's say 3 plus x, where will it go? It will go to 3, because we are only worried about the constant. Rest of them, it's going to be eliminated. So note that, therefore, the image of the evaluation map is the whole R, because I take any element of R, well, constant polynomial evaluation at the constant polynomial will give the result. Okay, now what is the kernel? So by the definition, kernel is those polynomials, let's say f of x belongs to Rx, just I'm writing the definition, such that evaluation at 0 of this polynomial must be 0. Means what? No constant term. So write f of x in Rx such that f of 0 is 0. So there is no constant term. So that means it is multiple of x. So this, therefore, yes, this is conclusion. So this is, because you can see, right, everything which has no constant term must be multiple of x, and any multiple of x is anyway evaluation at 0 must be 0. So this is this. So by isomorphism theorem, by the isomorphism theorem, what we get? We get that Rx modulo the kernel must be isomorphic to the image. Okay, well, just rewrite this because we already constructed the kernel. This is x and this is, because image is the whole R. So now you can see that the quotient is a field. So this will imply that x is a maximal ideal. Okay, I hope it is clear. All right, I want to give another example that also we saw yesterday. Now I want to consider, okay, A to be Rx, and I want to consider a new ring AY. Okay, so basically this is Rx over Y, that we saw that it was Rxy. Okay, and then you consider the ideal x comma y. Okay, this is ideal. So our claim is that this is also maximal ideal. This is also maximal. Okay, so how do you show this? Yeah, so what you do is you can have the same evaluation map, actually 0 comma 0 from R xy to R, what do you do? Well, I have a polynomial in two variables. I will evaluate at 0, 0. Okay. So again, the same reasoning will tell you that, note that, or in fact, actually, I will encourage you to check this, verify. This is a ring homomorphism. It's actually very easy. Actually, I kind of told you last time, so same thing will work. So this is a ring homomorphism. Now, again, same reasoning, because the constant polynomial are still here. So I can have the image to be the whole real numbers. That is also there. Furthermore, the ideal generated by x comma y is subset of the kernel. Why? Because, okay, it's easy. Because anything which is in the ideal, let's say h belongs to ideal generated by xy. So what does it mean? H must be of the form x times f plus y times g for some f and g. So therefore, if I evaluate at 0, well, x will annihilate this part, y will annihilate that part. Okay. So this fellow, this ideal should surely is in the kernel. Now, as always, we want to show it has this is equality. So we show that this ideal is precisely the kernel. Okay, precisely the kernel. So how do you show this? Well, so begin with any element f in the kernel. Okay, begin with any element f in the kernel. Now I'm going to apply. We apply the general division algorithm to what is the ring? AY. Remember, A was Rx. So the coefficients are from Rx and it is Y. And remember, so I want to divide by, so f of xy. This fellow, I consider it as a polynomial in Y. The coefficient are from Rx. Now this qx times y. Remember, there is no component here. So let me go back above. Yeah. So in general, there is a part where it is some power of element comes into picture. But what was that element? It was a leading coefficient of g. However, our g in this case is y. So leading coefficient is 1. So we are good. So yeah. So qx times y plus r of x comma y. Remember, because I have to write x comma y because it is a coefficient from a. We have this with what is the condition? The degree, y degree of rxy is strictly less than 1. That is the y degree. So is 1 means what? It is basically a polynomial in x. Okay. Now use the fact that now evaluation at 0, right? So 0 is equal to f of 0, 0 is equal to r of 0, 0. Is that correct? What is r of 0, 0 is equal to 0? Remember, this will imply that rxy is in fact is a polynomial in rx. So in fact, no need of, because y degree is less than 1. So there is no y component. So therefore, this will imply that now you have root, right? X. So therefore, x must, so okay, can, so therefore this will imply that rxy is basically x times some q, maybe q dash. Okay, x times some q dash, some polynomial, doesn't matter which one, right? So therefore, what we have is look at the equation. This equation I will rewrite because r I have written as a multiple of x. So this means f of xy is equal to q times y plus q dash times x. So this is of course in the ideal generated by xy. Okay. So therefore now again by the isomorphism theorem, what we have? We have that rxy modulo kernel which was generated. This is the whole ring overfilled. So therefore we have that x comma y is uh, is a maximal ideal. So you can see the power of this algorithm, division algorithm, which is more general. Okay. So any question? Okay. So let me now give another example. So same thing I want to do, that A to be the Rx and consider polynomial over A. Okay. So which is just now we saw xy. Now let's say P ideal generated by y minus x square. Okay. So it is generated by the polynomial. Now why I'm saying it is geometric? Because see, here also we are taking quotient. In the quotient, whichever ideal, we are declaring it to be 0. Okay, that's how it will be. So therefore, essentially, why if I want to quotient out rxy modulo ideal generated by y minus x square, that correspond to parabola. So this is parabola. Okay, so let this now first of all note that y minus x square is in the ideal generated by xy, right? Isn't it? Because it is, I can write it as y minus x square. Oh, okay, I will write. So y minus x square, I will write it as, well, y into 1 minus x into x. Therefore, it is in the ideal generated by xy. We just saw that this is maximal ideal. We just now saw. It is maximal ideal. So what we have is that P is inside xy. But note that it's easy to show, actually verify. P is properly contained in xy. Of course, for instance, x and y are the elements which are in the maximal ideal but not in ideal P. Okay. Now our claim is P, which is ideal generated by this polynomial, is prime. Okay. So as the question about the ideal which is prime but not maximal, here is the one coming from the geometry, basically parabola. Okay, so same kind of thing is favorite. Our this thing is evaluation at x. Okay, what is a map? So suppose I have a I x y to the power I. Where will it go? Well, it will go to a I x x to the power I. So simply oh sorry, I want to, so instead of y I want to take x square. Wait, evaluation at x square. Um, oh, this is okay. Where is it? 2i. Okay, whenever y is there, I will replace by x square. So evaluation at x square. Remember, a is rx. Okay, so same reasoning. this is a ring homomorphism. Okay, this is a ring homomorphism. Furthermore, same reasoning again, ring homomorphism, and the image again you take the constants. Now remember, it is constants where in AY, so they are elements of A, well, which is Rx. So evaluation map, it's the whole ring A, which is Rx. So it is surjective actually. Now let's find the kernel. First note that if I evaluate this polynomial y minus, so this is 0. So this will imply that the ideal generated by this is inside the kernel. Yeah, this is the easy part. Now as usual, converse part requires some proof. So suppose that let's say fxy belongs to the kernel. Okay, suppose it is in the kernel of x square. So we apply general division algorithm with, you know, g is equal to y minus x square. Now again here the coefficient, see this we are considering where ay, x square is constant in ay. So you are considering, so again the coefficient of y is 1. So therefore what you get is that f of xy is equal to q times y minus x square plus r of, again I can write actually r of x only, or technically I should write r of xy with the condition again that the y degree of rxy is less than 1, which is the y degree of y minus x square. Less than 1 means there is no y term in this fellow. Okay, now this will imply that again you look at the evaluation map. So instead of y you replace by y square, because f is in the kernel. So you get this is equal to r of x square. Now yeah, is it clear as of now? Okay, so what you get again? So again r of xy, okay, so this will imply that r of x whatever, okay, so I should say that because again this is this is a root, but you can see that what is happening is that you have rx x comma x square, which is 0, so everything is x. So this polynomial, remember, okay, this I will tell you, this imply that r is a polynomial in x. So that variable na x square is actually kind of redundant. So this will imply that r is actually 0. That's what r of x is 0. So r is 0. So therefore the equation again, the star equation star will imply, because r becomes 0, f of xy is actually q times y minus x square. This is belongs to ideal generated by this. So therefore by the isomorphism theorem, what will happen? By the isomorphism theorem, f of isomorphism, okay, the kernel of the evaluation map is precisely the ideal generated by x square. Sorry, this is not by isomorphism theorem, and this will imply that by the isomorphism theorem that r xy modulo the kernel, which is ideal generated by this one, is actually isomorphic to R of X, which is A. So from here also you can conclude that of course this is an integral domain which is not a field, namely there are many non-invertible elements here, right? So of course y minus x square is prime but not maximal. Okay. Okay, any question? Okay, so let me give one more example. So I want to concentrate more on examples. That's theory we can develop, but it will take more time. So let me consider this ring. So what is it? So this is n upon m such that n is any integer and m is not in 2z. Okay, inside Q. Okay, you understand the set. So it is a subset of Q. In fact, actually, we'll see how it is a subring. It is a subset of Q such that numerator can be anything, but there is a condition on the denominator. I don't want denominator to be multiple of 2. It should not be even. So denominator is always odd. Okay. So first of all, it's actually verify that this is A is a subring of Q. Okay, Q is a ring, right? So it is a subring of Q. Okay, so what will be the maximal ideals? That's the question. So I will uh, write one. So let M be the following. What is it? Twice n divided by m such that, well, n is any this thing and m is in, of course, not in 2z. So what I am doing, I am considering a subset of A. In fact, this is an ideal. I am considering what I am doing. I'm not taking now that numerator is anything. I'm taking numerator to be even and denominator to be odd. Remember our ring, numerator can be anything, even or odd, but denominator always odd. So this I'm taking. So it is very easy to see that this is a this is an ideal. Okay. Now I claim M is the only maximal ideal. Only maximal ideal, not just it is maximal ideal. There is no other. Okay. So first of all, let's see maximality. So this is, I will leave it to you. Verify that this is an ideal. Okay. It's okay. So let's see now. Okay, so yeah, maximal ideal. What we have to see, there are various ways. Just now I have showed about the quotient rings, right? Quotient ring. If the quotient ring becomes filled, then we are done. In this case, actually, I will show that also, but just by using the definition, let's see, we can say. So what was it? First of all, it must be a proper ideal. Okay, that was, note that. For instance, 1 upon 3 cannot be in M because 1, the numerator is not even. So this will imply that it is a proper ideal. Okay, in fact, many other things, 1 over anything, 1 over M, where M is an odd will be. But anyway, this is a proper ideal. Now what we have to show, if I have an ideal which contains M, then it is either M or A. So let's say, let I be an ideal of A such that M is properly contained in A. Okay. So then we need to show that it is a whole ring. That's the idea. So how do you show that? Now note that, so there exists some element X in I. I'm just writing set theoretic such that X is not in M, right? This is a something is not subset. So X belongs to I such that X is not in M. That is so X is not in M means what? The numerator cannot be even. So that is there exist A and B to be integers such that A cannot be multiple of 2 and B, because cannot be multiple of 2 with X to be A upon B. Okay, is this clear? Because X is not in M. So X is not, see, any element, of course, it is a part of rational. So any element will look like numerator upon denominator. So our ideal, this chosen ideal is such that, well, numerator is always even, denominator is odd. So something is not in ideal M means such a thing. Now note that thus A comma B is a unit in A. Okay, why? It's actually easy. So note that A upon B, okay, belongs to A first of all, and A also this. So therefore B upon A belongs to A as well. Remember our definition of A. It is a collection of all those rational numbers whose denominator is odd. That's it. So here though A and B both are odd. So of course I can invert B upon A, I can write still in A. Okay. So therefore this implies that because you have ideal containing unit, so ideal becomes the whole ring. Okay. So this is, that's what I showed, right? This is a maximal ideal. Actually exactly the same reasoning will tell you that there is nothing actually that I will show. In fact, the above proof argument also shows that every element X in A but X is not in M is a unit. That's what actually we showed. It's not much about ideal, but we shown that if there is element which is outside M, X is not in M, then it becomes invertible. So is a unit, and therefore hence, so therefore cannot be, because there is no other distinct ideal. So therefore hence there is no other maximal ideal. Okay, so unique maximal ideal. Is that clear? Okay. Yeah, so okay, now I will give another proof. So let me, so what you do is, in fact I will show that now. Let us show that this A modulo the maximal ideal is isomorphic in fact to Z mod 2Z, just two element set. As you can actually see by the way it is defined, right? It is only about whether numerator is even or whether denominator numerator is odd or even. That's the only thing. So what we'll do, what you do is that consider the map phi from A mod M to Z mod 2Z. How does it map? So given A, okay, maybe given yeah, A upon B plus M, okay, A upon B plus M means simply ideal. I think above I have defined just multiplication type. So let me write like this, the coset, right? Because we are in the, yeah. So A upon B M. So yeah, I should have written A plus B above actually. So let me change that also. Somehow I forgot to write in the coset, right? So let me go back where the quotient is defined. Yeah. So A plus B, A plus B. So this is, yeah, this is the standard notation. I don't know why I wrote like multiplication, but anyway. So let's come back. So where do you map it? So as I was telling, actually the numerator, it's always odd, not playing much role, but well, it plays a role, but as of now. So what you do is simply consider A plus 2Z. Okay. Simply consider A plus 2Z or A remainder, or this is same as our earlier notation A. So remainder of A after dividing by 2. So basically it will tell you when it is odd or even, that's it. So first of all, let's check whether it is well defined. Is phi well defined? Because remember we are in a coset. If I choose a different coset, then what will happen? Okay, so well defined. If let's say A upon B plus M is equal to A dash upon B dash plus M. What does it mean? Then by definition their difference belongs to M. That's the definition. So what is the difference? Difference you can write as B dash A minus B A dash divided by B B dash is in M. So something is a M means what? The numerator has to be even. Is congruent to 0 modulo 2. Okay. Now note that, yeah. So basically it says that B dash A is congruent to B A dash modulo 2. But note that, see, these are B and B prime. These are part of A, and that means B and B prime are odd, are not divisible by 2. Okay, they are not divisible by 2. So what does it mean? A and A dash are congruent modulo 2. Correct? So therefore mapping is well defined. This will imply that phi is well defined. Now actually rest of your, it's easy. If I have a, this is a ring homomorphism, that also you can check. That I will leave it to you, this straightforward thing. Verify that phi is a ring homomorphism. Now again, it's easy to check that because 0 upon 1 maps to, okay, but m phi of this is actually, well, 0 bar, and phi of 1 upon 1, of course, this is 1 bar. So this will tell you that phi, so image of phi means phi is surjective. Image of phi is the whole ring. Okay, then what is the kernel? So the kernel of phi, let's write down, it is a upon b plus m such that this is 0, numerator has to be 0, where in z mod 2z. Well, that means that it should be multiple 2 times, let's say, a plus m. Oh, wait, I will rewrite it. So this is all a upon b plus m such that, sorry, a belongs to 2z, so multiple of 2, which is actually the precisely the definition of our ideal m. So by the isomorphism theorem, what you have, we have that a modulo the kernel, which we just showed that this is isomorphic to z mod 2z, correct? So this is another proof that m is a maximal ideal. Okay, okay, is there any question? So it is another interesting thing about this ring. In fact, this is the only prime ideal in M. No other ideal. Okay, this is the only prime ideal. That is also a thing. So that I will also give you. I will not prove, but let's see. What shall I write? Okay. Remark. In fact, M is the, okay, anyway, I will don't write because anyway I'm not going to give proof, so let it be, but interesting anyway. Okay, any question? Okay, so some so similarly actually you can so exercise maybe I can give. So you consider the ring, actually it's very similar, just you follow the same reasoning. So let me generalize it. So let p be a prime number. Okay, let's say this is a prime number. Now you consider ring A to be a upon b such that a can be any integer, but b it's not divisible by prime p. Okay, again a subring of q. Okay, then show that first of all a is a ring. So same kind of exactly same in fact proof. Then show that m, which is p times n divided by m, such that n can be any integer and m is not divisible by p, is the unique maximal ideal of A. Exactly same actually in the whatever we did, just replace 2 by prime P. So everything will work. And of course, similarly that A modulo M will be isomorphic to Z mod PZ. Okay. Exactly the same thing actually. Replace, actually if you blindly even replace 2 by P, proof works. All right. So let me, because I have supposed to give you some relation related to the nil radical. So definition again, let A be a commutative ring with unity, of course. Okay. The nil radical of A. So we denote it by, well, nil A is what are this? So all A in A such that A power n is 0 for some n depending on A. Okay, so these are nilpotent elements, if you know what. So what we say that, okay, in a commutative ring, nil radical is all those A such that some power of A will vanish. Okay, becomes 0. So that is a definition of nil radical. Okay, so very first thing immediately we can check. So remark is that the nil radical A is an ideal. Here in fact actually commutativity is used. So it's easy actually. For instance, if A and B are there, right? So A and B belongs to nil radical. So not really the proof I want to give, just the outline. A and B, then A to the power n is 0 and B to the power m is 0, something. So then K you take sufficiently large, okay, some m and n such that you can actually choose K. A plus B to the power K will be 0, right? See, A plus, now here commutativity is used. So A plus B, you are going to use this binomial theorem. Therefore, you can make sure that every time the power of A and power of B will go beyond n and m. So that's it. So that you can choose. So, okay. And of course, A into B, you can just choose m n. Because of commutativity, this will happen and this is 0. Okay. So basically that's the outline of proof. So nil radical is an ideal. Okay, so for instance, if you have an integral domain, in an integral domain, you won't get any nil radical. Means it will be 0, just the 0. Okay, so now there is some, what you call, maybe proposition. Proposition is the following. In terms of prime ideals, you can classify. So I will use the same notation. So let A be a commutative ring with unity. Then the nil radical of A is the intersection of all prime ideals. Okay, intersection of all prime ideals. So take any all possible prime ideals in a ring, intersect them, you will get the nil radical. So let us prove this. It's not difficult. So okay, so let me write. So let I is equal to the intersection of P, where P is prime. Okay, let's the intersection of all prime ideas, let's call it I. Okay, so one way is always obvious. So if I have element A in the nil radical. Sorry, nil radical of A. That means what? There exists some natural number such that A to the power n is trivial. Okay. Now 0, this will imply that A to the power n, which is 0, 0 belongs to every ideal P. So this will imply that A belongs to P, the property of prime ideal. Okay. So this implies that A is in I. So this is for every P for all prime ideals. Correct. So this is, so what we essentially did, so this implies that the nil radical is contained in the intersection. That is the easy part. Other part is also not difficult, but little bit more is required. Okay. So now our aim is that given any element in the intersection, we will show that it is in nil radical. Now, to show that this is in the nil radical. So this is equivalent to saying that equivalently we show that if some element is not in nil radical, then A cannot be in I. Okay, this is equivalent statement, right? P implies Q is same as not Q implies not P. So we'll show this A not in this. Okay, so what does it mean? So note since A is not in nil radical, therefore sorry, not in nil radical, A to the power n is non-zero for any natural number, right? Yeah, you can take a non-zero also, right? Of course, you can take a non-zero element here. So because for suppose there is a any natural number such that A power n is 0, means it is in nil radical. What we want to show is that we begin with something which is not in nil radical, and we will conclude that A is not in the intersection. So again, what we want to show, A is not in intersection means there is at least one prime that will avoid A. Okay, so our aim is to find a prime ideal not that will not contain A. Okay, that's the idea. Now the standard proof is the following. Consider the set of sorry, एक minute. So consider a set of, let's say, ideals A such that what will happen? Can anybody want to guess? Okay, so A is such that A to the power n does not belong to A for any n bigger than. So no matter which power you take, okay, that should not be an ideal. That's the matlab. That's what we do. Now note that this is non-empty. Why? Because, well, we have chosen A where A power n cannot be 0. So 0 ideal is certainly there. Okay. Now you know what we are trying to do. So we want to apply John's lemma. So same thing, verify this. I will again leave it to you. That every a chain in sigma has an upper bound. Actually the same thing, because upper bound, what you do is in sigma you need to have a partial order. Here also you do the partial order by inclusion, so the union will work, so it has upper bounds. So by Zorn's lemma, sigma has a maximal element, let's call it P. Now this is our claim that this will work. This is a prime ideal that will avoid A. So claim is that P is prime. Okay. So how do you proceed? Just one moment. How do you proceed? So standard technique. Suppose not. So let x comma y in A be such that x into y belongs to P, but neither x nor y is in P. So um, you begin with xy in A such that x into y is in P, but neither x nor y is in P. Okay, is this okay? So now consider again, consider the ideals generated by P and X, and consider P and Y. Okay, ideals in A. So what is a typical element? This is of the shape uh, what shall I write? Maybe Z plus W times X kind of thing, where W can be anything. Z is in P. Okay, like this. So this is this is the smallest ideal containing both ideal X and P. That's how addition. Okay. Okay. So consider this ideal. Now what can you say about this ideal? Yeah, so this is a ideal. So note that both P plus X properly contains P. That is the assumption. X is not in this. And P plus X, sorry, Y properly contains P. So by maximality, we can choose K, say natural number, such that some power of K belongs to both. Right, because maximality, see, this was this thing, right? These are the all ideals where no power of A in that ideal, but here we got ideals which are bigger than P, right? So therefore there must be some power. Now there are just two ideals, so we can take a um, large enough power, right? Large enough power for which both are. So what will happen now? So, or if you want, I can write different also. Okay, I can write different also. L and K, let's say. So what will happen? Then I multiply them. So this will imply that A power L plus K, where will it be? Actually, this will be, see, this is P plus X, P plus Y. I multiply them. You can look here. So, okay, so element will be like Z1 plus, let's say, W1X into Z2 plus W2 Y, right? So what is it? So well, it is Z1 Z2 plus W2 Y Z1 plus W1X Z2 plus W1 W2 X into Y. Now note that Z1 Z2, whenever Z occurs, they are part of P. So this whole thing, it's part of P. Another thing, by our assumption, X into Y is in P. So therefore, any multiple of X into Y must be an ideal P. So everything is in P. So we got this is in P, which is a contradiction because the choice a contradiction. No power of A is in P. So that's contradiction, and hence P is prime. And we are done. So we got the prime ideal, which is which is not this thing. Yeah, it does not contain our element. Okay. So any question? Okay, so anyway, I can define another thing which is very similar and easy to show. We can define the radical. So okay, let A be a commutative ring with unity, and let A be a ideal, be an ideal of A. Then we define the radical by definition is all those elements, let's say X in A, such that some power belongs to A for some n that may depend on X. Okay, so what we defined earlier was a particular case of this definition, radical of 0. So note that. So note that if this ideal is 0 ideal, then the radical of 0 ideal, well, this is actually the nil radical. Sorry, nil radical. Okay, and that's the thing, the generalization. And in fact, there is a result which is easy to show. Okay, so let me see, proposition maybe. So radical of A is actually the intersection of prime ideals, but that contains A. Okay, earlier we said any prime ideal, but now we have to look at this. So basically the proof is easy because instead of A, we consider A mod A. You consider this because now here you are making A to be 0 in the quotient ring, but you require one more result that gives the correspondence between ideals of the quotient ring and the original ring. Okay, that I haven't taught, but anyway, so basically if you know that, then this becomes easy. Okay, another one. Anyway, I think it's almost time, so let me give one definition, and I will stop for some questions. So same notation, definition. So then Jacobson radical of A, okay, so is intersection of all maximal ideals . Okay, this is called maximal ideal. So Jacobson radical is defined in this way. There are many interesting things just related to Jacobson radical and nil radical. Okay, but anyway, so I think I have only 2-3 minutes left, so I can take some questions if someone. I will try to answer.
Sir, is it audible?
Yeah, sorry.
Is it audible?
I cannot hear you properly actually.
Second, sir. Sir, how to audible?
Huh.
Sir, one question from NRC.
Sir, good evening, sir.
Good evening.
So you explained very well to my doubts regarding maximal ideal parameters and including things. Yesterday, you clarified now very well. So thank you very much, sir, for giving an excellent picture today about maximalians, what it means, etc. So I have one question, small question about maximal ideals. So the conjugative ring with unity. So what can we say about nilpotent elements? When all have only maxified, only one maxified.
No, I cannot hear you actually.
Are they commutative ring with unity, sir?
Sorry, commutative ring
With unity.
with unity, huh?
Yes, if we have only one maximum ideal,
Okay.
then what are the important elements in this thing? Important elements, important elements.
Nilpotent elements where your ring has only one maximal ideal.
Sorry, sir, non-important elements.
No, it see.
Idempotent elements, sir. Idempotent elements.
Idempotent. So idempotent is it?
Yes, yes, sir. How many idempotent elements are in this ring?
So x square is equal to x.
Yes, yes.
And you have only unique.
Right.
Yeah. So it won't. So only 0 and 1 is the answer, because you know you have x square minus x. So it is x into 1 minus x is 0, right?
So okay.
Okay. Let me write it actually.
So can we put it easily?
Sorry.
You can do it easily, sir. Easily.
Yeah. So so let A be a commutative ring with unity with 1, let's say, and let's say M is the unique maximal ideal. Okay. And let you know x belong to A be such that x square is equal to x. Correct? Okay. So what happening is now, okay, so note that this imply that x into 1 minus x is 0, right? Yes. So what will happen? See, this is uniqueness of maximal ideal that you want to exploit. Any guess how to do that? See, this unique is the, oh sorry, I have written not M is the unique. Uniqueness is important. Anyone wants to guess? Uniqueness, how do you you know exploit? See, okay, so 1 minus, see, for instance, 1 minus x, if, okay, let me write, if 1 minus x is not a unit. Okay, suppose it is not the unit. What does it mean? See, just now we saw because of uniqueness, na, this means imply that x minus x, sorry, 1 minus x must be in M. Because see, 1 minus x is not a unit, then ideal generated by 1 minus x must be in some maximal ideal, right? Any ideal is in the maximum. So, but here there is only unique one. So 1 minus x will be in the M, correct?
Sir.
Yes or no?
Yes, sir.
Yeah. So then anyone wants to take this further?
No, sir.
Sorry?
No, sir. No, sir.
No, means, okay, I'm saying that you will only have, what are the idempotents? You will only have either, so this will guarantee you that either, x is 0 or x is 1. That's all.
Would you take regarding analysis? Any
Huh?
questions?
Sorry?
Sir, I am audible, sir.
Yeah, but I cannot hear you properly. Okay, so let me,
Sir, good evening, sir.
एक minute, I will just complete. I thought, see, okay. So first of all, this will happen. So x is, remember x, because of this condition, x is not a unit. Okay. So this will imply that the ideal generated by x is inside M, correct? Because it's the only by uniqueness of M, right? So ideal generated by something must be in the maximal ideal, but there is only one. So this will imply that 1 minus x cannot be in M. Okay, otherwise what will happen? Otherwise x is already there, 1 minus x is there, otherwise 1 will be in M. So which is again. So actually we saw for the ring, right? Any integer upon the this. So because of uniqueness, you can, this requires some work actually. 1 minus x is a unit. Okay, what is that? It's just quickly, let me write. Uh, um, so anything, it's okay. So y is not in M. Okay, suppose y is not in M. This will imply that ideal generated by y, and this should be the whole ring because M is a maximal. So this is ideal maximal. So therefore I have one I can write in terms of what shall I write? Okay, z plus w times y, where z is in M and w is in A, right? So that's what you have. So whenever, so read modulo M. Okay, so if you read modulo M, then this is one is congruent to wy mod M. Okay, something like this. So just the idea.
Sir, is it audible, sir?
Yeah, you are audible.
Good evening, sir. This is my privilege to express our heartfelt gratitude to Dr. Abhay Soman, who serves as an assistant professor at SMS HCU. We are immensely thankful for graciously accepting our invitation and delivering an outstanding lecture on pendulums, homomorphism, and isomorphism on our ring theory. Despite your planning schedule, as a key resource person, your expertise generate great the training sessions at University of Hyderabad. Your lectures undoubtedly shed light on the core principle of audit theory, emphasizing its pivotal aspects. On behalf of the Commissionerate of College and Education, key resource persons, and all participants, I extend our sincere thanks to you, sir, for your profound insights and thorough explanation of the topics. Once again, thank you for your invaluable contributions.
Thank you very much. Thank you very much for inviting. It was pleasure to give lectures. So anyone has any questions or something, they can email me and find out. Okay. Thank you. So can I log out?
Yes, sir.
Okay. Thank you.
Thank you, sir.